signifies the amount of variability explained in the response by the regression model. We also say that R squared adjust is important. It has the same interpretation as R squared, and it is important when we are dealing with the multiple regression. Now, we also talked about the meaning of the intercept and slope. The intercept being the value of the response when the independent variable is equal to 0. While the slope, if you look at this equation, which is displayed on the screen, we have volume is equal to minus 36.9 plus 5.07. So the slope is 5.07. For every unit increment in diameter, volume increases by 5.07 because it is positive. If it was negative, then we would say for every unit increment in a diameter, volume would decrease. Okay. So that's what how we interpret the slope and intercept. So here is the interpretation of the F value, and the F value, that is the F ratio, which is the ratio of the mean square regression over the mean square error. And we are testing the hypothesis that there is no linear relationship between volume and diameter, while the alternative is that there is a linear relationship between volume and diameter. So we can use actually the tables, the F distribution table, to make conclusions about the null and alternative, but we can also use the p-value. In our previous table, we see that our p-value is 0.00. And our F value is 419.36. So we can use the p-value. So you see that our p-value here, 0.000, is smaller than 0.05. Then that gives us the evidence to reject the null hypothesis. And we conclude that there is significant linear relationship between volume and diameter. Now, if you want to use the F value, you go to the critical table, you go to the F distribution table and look for a critical value that intersects the denominator degree of freedom and the numerator degree of freedom. In this case, our numerator degrees of freedom corresponds to the degrees of freedom of regression, which is 1. And the denominator degrees of freedom corresponds to the degrees of freedom of the mean square error. So we have degrees of freedom 1,9 at probability of 0.05. And the value that intersects those two degrees of freedom is 4.18. Now, 4.18 compared to our calculated value is small. And since it is small, then we have evidence to reject the null and conclude that there is a significant relationship, linear relationship between volume and diameter. So whatever you are comfortable with, either the F value or the P value, but it is very easy when we are writing manuscripts to use the exact P value. If you're writing your manuscript or your project, indicate the true P value from your data. Don't just say P less than or P is greater than, okay? So make sure you indicate the right P value. So there's an exercise here for you, but later on you can do it at your own pace. And there were 9 samples of soil prepared at various amounts of inorganic phosphorus and then applied to the soil. And they wanted to see how much is absorbed by the plants. So the absorbed phosphorus was measured after 38 days. So you will do that in your free time to be able to practice. Let us look at the residuals. In the chart, any query? Okay, you seem to be fine. Any problem in the chart? Okay. Okay, let's continue. The residues. Remember yesterday we were saying that residues are deviations of observations from the fitted value or predicted values. And we get the predicted values from the line of best fit, which is estimated by the least squares estimate. So these residues are important, as we saw yesterday, in estimating the mean square error, which we use for testing whether there is a linear relationship between the response and the independent variable. So here we find that statistical inferences can be made when the postulated model is adequate. And a model is adequate when the residuals are assumed to be normally distributed with the mean 0 and standard deviation sigma. That is one of the assumptions. The other assumption we make is that the residuals have constant variance and no correlations, meaning the residuals are independent. We also assume that there's a linear relationship between the response and the independent variable. Okay, so we can test those assumptions to see whether our model does not violate them. If the model violates any of the assumptions, then we have to do something to make sure that all the assumptions are valid. So for us to test that residuals are normally distributed, we use a histogram. You construct a histogram of residuals, and in case you get a bell-shaped curve of the residuals, then the residuals are normally distributed. Or we use the normal probability plot of residuals versus normal score. So if all the points fall on the straight line in the normal probability plot, then the assumption of normality is valid. We are going to see this. To check the assumption of constant variance or constant error variance, a plot of residuals versus fitted value is constructed. And we see that if we get a plot like this, you can see that these points, the blue points, are just a random scatter of points. There is no what? Pattern in the residuals. So in that case, residuals have constant variance. Okay. Now, if the points form a horizontal band around 0, then the assumption of constant variance is valid, just like we said. If the residuals increase with increasing fitted values, this indicates the error variance increases with increasing response. Therefore, there is no constant variance. If residuals form a schematic pattern, then we also say that the linear model does not fit the data. So a plot of residuals versus order, time order, or order of observation helps us to detect whether the residuals are independent, meaning the residuals are not correlated. So if there is just a random scatter of points, then the residuals are independent. So we will see this more in the practical, which we are going to do today. And you're able to see what it means when the residuals are not, do not have constant variance. So if the assumptions are violated, we can either transform the response or the independent variable. Normally, we can use the natural logarithm or square the response or the independent variable. Sometimes you find that the linear model is not appropriate. In that case, we use a polynomial regression, which is a special case of regression where we have powers attached to the independent variable. Okay, so I want to, let me see whether I can write, yes. So what I was saying that I'm going to write in the notes and hopefully you can see. In case we have something like this, this is our epsilon residuals. And here we have a 0 point, because some are negative and some are positive. Here we have our fitted values. Now, for you to know that we do not, the model does not fit, we can get something like this. So something like that. So you see that if you get such a graph, hopefully it is visible. That indicates that the linear model doesn't fit data. You can see the residuals are increasing with fitted values. These are fitted values Y here. Our Y is a fitted value. So that shows that there's non-constant variance. The linear model does not fit our data. Then we need to use the polynomials. Now, how does a polynomial model appear? Okay, our polynomial model has a slope. So this is our slope for the linear term. Then if you want to fit a quadratic, we are going to have our independent variable squared. So hopefully that is clear. Sorry about my handwriting. And the x squared signifies a quadratic model. The x squared signifies the quadratic model. And if you get a graph like this one, then we can try to fit a quadratic model, and that falls under polynomial regression. Okay, hopefully that is clear. So I'm going to remove this. Okay. So I want us to talk about multiple regression theory. Then when we go to do practicals, we do practicals on all of them at once. What do you think? Should we do that, or we talk about, do we have materials for today? Yes, they will send the materials. Yes, they will send the materials for you for an isovariance. And also the updated script of generating designs will be sent today. Okay, so let's continue with the multiple regression. They will be sent in the Google Drive. Let's continue with the multiple regression, and then we do practicals at once. Okay. Now, sometimes you find that you have so many factors, and also the unexplained variation is large. For example, if you find R squared is equal to 40% after running a simple linear regression, where you have only one independent variable, then that signifies that there are other factors that are not in the model that you need to include so that you explain most of the variation. So that means that you have to include more than one independent variable. So a regression model where we have one response and two or more predictors is called multiple regression. And this is the multiple regression model. We have many slopes, one intercept, okay? So under the multiple regression model, X1, X2 are independent variables, and while beta I are unknown parameters, the intercept and the slopes. Epsilon is random error due to other factors not included in the model. Now you remember the assumptions we mentioned under the linear relationship still hold even under multiple regression. And in addition to that, we also assume that the independent variables are not correlated. So in addition to the assumptions under simple linear regression, for example, we said Y, which is the response, is linear related to X. The unknown random errors are normally distributed with mean 0 and variance sigma squared. The unknown random errors have constant variance. The unknown random errors are independent. And in addition to that, we also assume under multiple regression that the independent variables are not correlated. Okay. So this is an example of an output where we include two independent variables. So in this output, we see that this table shows us the linear model where we have volume, the intercept of -58, the slope for diameter and slope for height. Now, when it comes to multiple regression, for you to be able to interpret the slopes, we hold one variable constant, we hold one independent variable constant, and then interpret the other. Okay, so in this case, if we hold height constant, we are going to say that for every unit increment in diameter, volume increases by 4.71. Okay, then when it comes to height, we hold diameter constant and interpret that for every unit increment in height, volume increases by 0.339. Okay, so that's how we interpret the model for regression. Okay, so now here the output gives us the coefficients, the standard deviation, the t-value, and the corresponding p-value. The hypothesis we are testing here under multiple regression is that the two independent variables are linearly related to volume, or there is a linear relationship between volume, diameter, and height. And null is that there is no linear relationship between volume, diameter, and height. So when we look at our p-values, we see that the p-values are small for diameter, smaller than 0.05, and also for height, indicating that there is a significant linear relationship between volume, diameter, and height. Now, in this case, we are going to interpret the R-squared adjust, because R-squared, the coefficient of determination, increases every time you add in a model. Every time you add in an independent variable. So R-squared adjusts for any parameter added in the model. So it is the one which is more appropriate for comparing models or for assessing whether the model fits our data. So our R-squared adjust is 94.4%. This is quite strong. So quite high. We say that the variability in volume explained by a regression model is 94.4%, or 94.4% variability has been explained in volume by the regression model. Okay. So the analysis of variance, this overall, it is just testing whether there is a linear relationship between volume, diameter, and height overall. Then, if you're able to produce the sequential sums of squares, if you add these two values for diameter and height, you get the regression sums of squares. So the sequential sums of squares down here are just showing you how much is each independent variable contributing towards the regression sums of squares. So how much variability has been explained by diameter? in volume. So you see that diameter explains most of the variability in volume, and height explains only 102.4. Okay. Okay. So we've seen this, and there's also an example. So lastly, but not least, I want us to talk about indicator variables. And sometimes we have explanatory variables or independent variables that are categorical. But we would like also to include them in the regression. So in that case, we cannot straight away include categorical information in the model. So we code our categorical information and formulate what we call indicator variables or dummy variables. Okay. So how do we formulate dummy variables? So we look at the number of categories per independent variable. So assuming we have an independent variable like variety of tree, and then the varieties are 2. So the number of dummy variables that will be created is equal to the number of levels under the categorical variable minus 1. So if there are 2 categories minus 1, that implies we need only 1 dummy variable. If there are 3 categories, then we need 2 dummy variables. Okay. So how do we formulate the variables? How do we formulate the variables? So the qualitative variables have m levels. We need m minus 1 indicator variables to represent this variable. So let's see, assuming that we have an indicator variable. So our indicator variable is variety. And there is variety 1. I chose a vanishing pen. Sorry about that. Okay. Okay, so we have variety 1 and variety 2. We are going to put our independent dummy variable here. So for us to formulate the dummy variables, we are going to code variety 1 and variety 2 using either 0 or 1, whatever is appropriate for you or easy to understand. But in most cases, we use 0 and 1. So we say if variety is equal to V1, then variety is equal to 1. Otherwise, equal to 0. So we are saying if V1, if variety is V1, then we give it a code 1. Otherwise 0. That means under the dummy variable here, for V1, we are going to write 1. And under V2, we are going to write 0. Okay? That is in case you have only 2. In case you have only, in case you only have 2 categories. Okay. So assuming we have 3 categories, let me put 3 categories, V3. Okay, so we have V3. That means the number of dummy variables will be 3 minus 1, giving us 2 dummy variables. So we'll have dummy variable 1, then we have dummy variable 2. So let's see, how do we write these ones? This is dummy variable 2. Okay, so the first dummy variable in this case is that if variety equals V1, then the code is 1. Otherwise 0. That means that the first dummy variable Anything that is not V1 is going to be 0. So even V3 is going to be 0. So we got dummy variable 2. If variety is equal to V2, then the code is 1, then the rest will be 0. So we are going to represent dummy variable 1. I mean V1 as 0, V2 1, and then V3 as 0. So those are going to be our dummy variables. Then what you do in your regression model, you also include them in the model. And if you find that they are significant, that means that you need them in your model, and you can now include them in the regression equation. Okay. Any questions so far? How to change color? Okay. Okay, how can we know correlation between variables in regression? Okay. I'm just reading your questions. And then changing color in the GG plot, but we are talking about regression. We haven't gone to the R. Now you're bringing GG regression. Okay, so let me answer the question about correlation. How do we know the correlation in regression? We say that there's a relationship between the correlation and R squared. In simple linear regression, the R squared, when we get the square root of R squared, we get small r, which is the correlation. But on the other hand, we can actually ask for the correlation matrix in regression analysis. There's that option. So you can ask for the correlation matrix, and then you'll be able to know whether the independent variables are correlated. Now, for those who are talking about R, the GG plot, maybe when we go to R, we can answer that question. But meanwhile, my colleague Helen or Dr. Thomas can answer that question. How do we change color in the GG plot? Okay, there are some questions here in the Q&A. Can I use regression to test interaction effect of predictor variables? Yes, you can. Okay, you can use regression to test for interaction. Okay. What will be our criteria to select among 3 multiple regression models? Step up, step down, stepwise. Selecting a regression model, there are criteria we use. We use R squared adjust. We use mean square error. We use another statistic called CP, mal CP, and we also use press. Those are criteria you use to select among 3 models. But if you want to select the type of variable selection, it does not matter which one to use. You can use stepwise, you can use forward selection, you can use backward elimination, or best subset, or all subset. Okay? So if time allows, we are going to, I'm not very sure. I wanted to give 2 hours to your colleague, to my colleague, Dr. Thomas, to talk about analysis of variance. So let's see if he can finish analysis of variance today. Then tomorrow morning, before my colleague comes in, we can talk about model building. But for today, I wanted us to end at polynomial regression. Then I give a chance to Dr. Thomas talk about analysis of variance so that we balance. You receive knowledge from all corners. Okay. So tomorrow, then I can talk about model building, and my colleague, Dr. Helen, will come in with categorical data analysis. Okay. Okay. So hopefully I've answered your questions. And in case there's any question which is not answered, how can we develop dummy variables with 3 varieties? Yes, that's what I've been talking about. First of all, I said that a dummy variable is created for ease of Sorry about that. It seems like the network went off. Let me share again. Okay. So we were talking about the dummy variables. So in case you have 3 levels, that means you need 2 dummy variables. And we say that if I can write again, V1 here, V2, then V3. Then we have D1, dummy variable 1, then D2. Reason why we have 2 dummy variables is because we have 3 levels. So we are saying if variety is V1, then code it 1. The rest is 0. So these ones will be 0. And this one also 0. Okay. If variety is V2, then it will be called 1, the rest is 0. So V2 is 1, the rest we call them 0. Okay, so that is what is going to happen. And when you're running your regression model, you also include in dummy variable 1 and dummy variable 2 in your model. Okay, so that is indicator variable. We shall see. It's very interesting to see it practically. So let's see. Under indicator variable, we have what we call single line, parallel lines, and different lines. Now, in case you fit a regression model, even when you have categorical variables, but you find that the dummy variables you put in are non-significant, that shows that actually you don't need a variable to separate the varieties. You can fit one model onto your data, and it can be used to predict for all varieties. That is what we call a single model. Parallel models is when you put in these 2 dummy variables you've created, you find that they are significant, meaning that you need different intercepts, but the slope is the same. So in that case, we are going to have something like this parallel model for V1, V2, V3. Okay. Different, same slope, different intercepts. The intercepts would be there. So this is our graph. Okay. So we see that the intercepts are going to be different, but the slopes are the same. Okay. That is parallel lines. Different lines is when you have different intercepts and also different slopes. Let me erase this. So we are going to have different lines. Okay, so we can have such, we have another crossing here and another going like that. So this one will cross until it meets the y-axis. So meaning you have different slopes. The slopes are different. And also the intercepts are different. That is what they call different lines. Okay. Okay, so let's see next. So we talked about polynomial regression, and I said that sometimes you find that the data is not linearly related the independent variable and dependent variable are not linearly related. For example, this is the tensile hardwood concentration and tensile strength is the data which we are going to use in our practical. And we see that when I plotted this data, I found that it has a curvilinear relationship as seen in the scatter diagram. Okay, so this is the relationship you see. So if you fit a linear model, the model is not going to explain all the variability. So that calls for you to fit either quadratic or a cubic, depending on what suits the data. Okay, so in that case, linear model does not fit our data. And in case you ignore this pattern and fit a linear model, the first thing you notice is the amount of variability explained will be small. Secondly, the regression, the residuals are, the assumptions under linear model are going to be violated. So we shall see that in R, what happens, okay? Okay, sometimes you find that there is a nonlinear relationship, but it requires transformation, okay? So in that case, you can transform your Y or your X as well by either using square root or natural logarithm. And in case you have count data, for example, number of birds, number of leaves, number of trees, they don't follow a normal distribution. So you can use the square root of Y to transform the data or natural logarithm of Y. And if you have count data less than 0, then you use the square root of Y or square root of Y plus a constant. Then if you have proportions, percentage of people who said yes, percentage of people who said no, you can either use the arc sign in bracket square root of Y, or you model the distribution of the data. So you will find that tomorrow when my colleague Helen talks about logistic regression and log linear, sometimes you decide to model the distribution of the data instead of doing log transformation, because then you will be accounting for the distribution of the data instead of just transforming to make it linearly related to Y. So if you have proportions, you can use the logistic regression. Counts, we can use the Poisson regression. And in case of any other distribution, for example, Y-bar, you specify that distribution in your analysis instead of transformation. Because one thing, disadvantage about transformation is that when you come to interpret the slope and intercept, you have to back transform, which is so difficult. Or when you want to do predictions, then you have to do back transformation. After predicting, you have to bring them back to the original units of measurement to be able to explain such information in your manuscript or to the audience. Okay. So nonlinear regression will be talked about by my colleague Helen. And this is when we want to look at the distribution of the data, as I've just mentioned. And in case you want to see more about logistic regression, there's a simple book you can download online called by Montgomery and Parker. They give you a lot of details about logistic regression. For now, I think we'll stop with our theory, and we are going to open our script called core and reg in R, and go through all those practicals to see really what regression is in a practical term or in R. Okay, so in the chat, let me see if there's any question. I believe my colleague have been answering. We have a problem of analyzing. Please put the questions in the Q&A. My colleague says it's going to sort out the questions. Thank you very much, Dr. Thomas. Let's go to R. So your questions will be answered as we do practicals. Thank you very much for listening. And let's go to R. Let's turn our guns to R model programming. Okay. Okay. So please go to R, open your R script. You received it yesterday in day 5, and I'm also going to look for mine. Helen, can you share the Google Drive? Some people need to download information. You can repost it again. Okay. Okay, in the chat, has everybody opened their R script? Okay, the Google link has been posted in the chat. Please post it also in the Q&A. Montgomery and Parker, Introduction to and Parker. It's called Introduction to Regression. Okay, so let's start with a practical. Remember that the first thing we do is to load our libraries that we are likely to use. So I'm going to load all these libraries. And in case you see any library that is you've not installed a package, please first install the package. For example, if you don't have OLSRR, install it, gmodels, HIMS, gplot2, please install first. We just use the command line install.packages. In inverted commas, you put in the name of the package. And after installing, you run, you click the run button. And if you get red, don't get scared. So long as it doesn't say not installed, if it says installed or the package is okay, then you don't need to worry. Then let's set our working directorate. Now the working directorate is where you have your code and also the data sets. We are going to use a data set called egg, another one called, I think, indicator. Yeah, there are 3 data sets that we are going to use. And one is called polyreg. So make sure we set our working directorate to the folder where you have the data set. So for you to set the working directorate, go to session, set working directorate, and then choose directorate. Okay. So once you click that, we will browse. Mine is in day 4. So that's what I'm going to look for. So I click day 4 and then click open. So after setting the working directorate, we are going to read in the data called egg P, which is egg production. So using the line 30 and 31, let's read in our data. So I'm going to run line 30 and then run line 31. So when you read in your data called egg P, and then egg P prints all the data set. In case you want only the first 6, then you use head in bracket egg P. So this data set has water uptake, food uptake, and egg production. Okay, so are we at that stage? Let me check in the chat. Okay, so should we continue? Okay. Okay, thank you. So let's continue. So remember that under regression, the descriptive statistic or exploited data we use is a scatter diagram and correlation. Egg production is number of eggs. Food uptake is in kilograms per bird, and water uptake is milliliter per bird. Okay, so let's go to line 40, and we would like to construct a plot, scatter plot. So here I've given you 3 ways you can use plot: egg, $ food uptake, comma, egg P, $ water uptake. Then you can use either scattered or smooth or ggplot. So all of those give you the same plot. So the first line, which is line 40, if I run it, it shows us that if you look at it, we see a linear relationship between water uptake and egg production. Is the graph clear? Do I need to zoom or I don't need to zoom? Is the graph clear? Do you see the graph in the bottom corner? Okay, thank you very much. Okay, so I'm running the next code of constructing a scatter plot. You can see that the smooth, scattered or smooth indicates a line. It puts a line, or superimposes a line onto your data, but still shows us that egg water uptake is positive and has a strong relationship with the food uptake. Then the last one is when we use ggplot, and we run that. So ggplot, it plots our blue points are observed. The blue line is the fitted line. It is trying to show you if you fit a line. And we have named our Y as water uptake and our X as food uptake. Then you can split the command. You see this command here has been written at a go, but can be split, and you write those. I'm not going to run that bit. Let's go. You can run those in your free time. I wanted you to know that you can actually split the above command into step 1, step 2, step 3. But let's go to the next step, which is line 89. I mean line 90, where we are running the linear model. Now, even here, there are 2 ways you can run the model. You can use LM, which is linear model, then put in your y-axis, which is water uptake, is a function. You can see the tilde there shows that water uptake is a function of food uptake, and the data set is called egg P. Now, model is the object name. It doesn't have any meaning. It's just the name of that particular line, 91. So let's all run line 91. When you run line 91, it doesn't give you an output, so you run the model. The model only gives you intercept and a slope, but we want the summary of the model. So you run line 93 to give you the summary of the model. So let us focus on to the output and see what it means. So let's focus on the console and a summary review of the results. We find that we have coefficients. We have the intercept and the slope corresponding to food uptake. The intercept is minus 63.51. That is the value of water uptake. When the bird has not taken food, it appears like, does that mean it doesn't take water or doesn't need water? The negative sign. That one we need to go into the biology and find out what does the negative sign signify in that process. When it comes to food uptake, when for every unit increment in food uptake, water increases by 2.733 milliliter. So every time you put in 1 gram of food, then the bird is going to take more 2.733 liters of water. The hypothesis we are testing is that the null water uptake is not linearly related to food uptake. The alternative is that water uptake is linearly related to food uptake. Now, when we look at the p-value corresponding to food uptake, it is 4.02 times 10 to the power minus 8, which is smaller than 0.05. So that it shows that there is significant evidence, or there is evidence to reject the null and conclude that there is a significant relationship between water uptake and food uptake, or there is a significant linear relationship between food uptake and water uptake. Then after that, we go to look at the coefficient of determination, which is R squared. In this case, our R squared is 0.956. This means that 95.62% of the variation in water uptake has been explained by the regression model, or it has been explained by regressing food uptake onto water uptake. Okay. Any question in the chat? Any question? Prof, you're too fast. We are rushing to... Okay, sorry about that. Okay, I'll recap. What if there are two functions? What do you mean by two functions? Do you mean variables? Mohammed? Okay, two variables. Then we'll keep one constant. We are going to see when we have two variables, two independent variables, we keep one constant and interpret the other. Okay, let me repeat. So the summary model, you now know how to get the summary of the model. And we go to the coefficients. That's the most important bit. It gives you the intercept and the slope. So when you're writing your regression equation, it's going to be water uptake is equal to minus 63.51 plus 2.73 food uptake. And what does it mean? For the intercept, that is the value of water uptake when there is no food uptake, when food uptake is equal to 0. That means when the bird does not take in any food. But the negative sign in this case, we need to read about the biology. What does it mean when you have a negative intercept? Does it mean that the bird doesn't take water? No. The bird takes water whenever it wants, even if it has eaten or not. It's like a human being. It does not necessarily mean that you only take water when you eat food. You will take water at any time. So the negative sign there, we need to look at the biology and confirm what it means in that system, the biological system of the bird and water. Now, the slope, for every gram increment in food uptake, the bird increases water uptake by 2.733 milligrams, or I mean milliliter. I repeat, for every unit food uptake taken by the bird, the same bird takes in more water by 2.733, or the water uptake increases by 2.733. For every unit increment in food uptake, water uptake increases by 2.733. Why increase? Because the value of the slope is positive. Then we are testing the hypothesis that there is no linear relationship between food uptake and water uptake. And the alternative is that there is a linear relationship between water uptake and food uptake. So then, how do we test that hypothesis? We look at the p-value corresponding to food uptake. It's the one corresponding to the slope. In case there is no relationship, then we are going to get a straight line model. The straight line model is where we don't have the slope. So if the slope is equal to 0, we have a straight line. So here, the value of p we are getting is 4.02 times 10 to the power minus 8. It is smaller than 0.05. Where do we get 0.05? It is the significance level which you set as a researcher to test your hypothesis. And it is the probability that we assume the null is correct. Now, anything smaller than 0.05 shows that there is evidence to reject the null and conclude that there is a significant relationship, linear relationship between water uptake and food uptake. Okay, so I assume that is clear. And in case you have any question that is burning, my colleague will inform me. So let's go to the next bit. So we can add our regression line onto the data if you want to add. So the next command line is adding a regression line onto your scatter diagram. So let's run that bit, line 113. And we see that has added a regression line. And you can also add a regression model. That one, if you look before, we indicated that. So in the script, there's some explanation so you can follow the explanation. Here you can add the confidence interval. Okay. Now, assuming you want to get an analysis of variance model, you use the AOV function in R to get an analysis of variance model. But we remember that we had assumptions. We stated that Y is linearly related to X. That has been tested by the scatter diagram. But we want to look at the residual plots and find out whether those assumptions we stated are valid, that the response is linearly related to X and it's a random variable normally distributed with mean mu and variance sigma squared. The unknown errors have constant variance. They are independent and also normally distributed. So for us to be able to do that, we run our model. I've put AOV, but it's also running a regression. So I'll just clear the console and also clear our graph section. Okay. So now when you run model 2, line 144, and you run the summary, it gives you the same output we had before. Now, this particular line 147 is specifying the way you're going to organize your graphs in the panel. and you're going to plot your residuals. So the second line, 148, tells you to draw the residual plots. So we run line 147 and then line 148. It is telling me that error in plot.new figure, the margins are big. So I'll go in and reduce the sizes by zoom out. So I'll zoom out. Okay, so I'm going to run plot again. So if you look in the plot section, let me zoom this out and share it so that we can talk about it. Okay, so you see that we had assumptions. The first assumption was a linear relationship between the response and the independent variable, which we can test using the scatter diagram. And we've already seen that there is a linear relationship between water uptake and food uptake. We also say that the residuals should be normally distributed with mean 0 and constant variance. We also said the residuals should not be correlated. Okay, so we have the plot you see here, the first plot you see on the top, the first top, on the left-hand side, the topmost plot, it says a plot of residuals versus fitted values. And you see that once you see there's a random scatter of points, that shows we have constant variance. Other authors say that if this red line appears to be horizontal, then there is constant variance. There's also a test for homogeneity of residuals. My colleague, Dr. Thomas, is going to talk about it. So I will talk about the plots. He will talk about the tests. So here we see that it's just a random scatter of points, no pattern in the residuals, and conclude that there is constant variance. The second graph on the right top corner is a normal QQ plot, a normal probability plot. Again, there is a test called Spheral test, which tests for normality of residuals. But once those observed points fall on the dotted line, then the residuals are normally distributed. You can see that there are some residuals that have been identified. Residual 11, residual 7, and residual 6. So the program is telling us that those residuals are high, but does not necessarily mean that they're outliers. So you just need to check them out. If they are wrongly written, then you correct them, but you don't need to delete them immediately. Then residuals, the last one, which is residuals versus leverage, it is checking whether any of these points are outliers. So in case any value, any point goes above these dotted red lines, both above and below, then those are outliers. But we can see that all our values are within these, within the dotted lines. They are not outside the dotted lines, both above and below. That is the graph on your right-hand side, bottom corner. So the dotted lines you see above here are like threshold for you to determine whether that particular residue is an outlier or it is high. So we see that our data shows that all our points are not, our residuals are not outlier. Okay. Then we said residuals versus time order gives us tests for independence. Okay, so I'm going to stop sharing and then share the R script. Okay. Okay, let's go ahead and talk about multiple regression. We said multiple regression occurs if you have a response and more than one independent variable. We are still going to use our egg data, but now adding egg production. So we are going to say we are going to model water uptake as a function of food uptake and egg production. Okay, so that is line 159. Remember, when you're doing regression, the first descriptive analysis is a scatter diagram, and you can also get the correlations. Okay, so let's run line 159. Okay, so I'm going to concentrate on the console. So if you look down at the console, we have our coefficients showing the intercept, the slope for food uptake, and the slope for egg production. So you can write your regression equation using these estimates. And we can interpret these estimates. So like, if we look at the slopes, we keep egg production constant and interpret food uptake. So in this case, for every unit increment in food uptake, water uptake increases by 3.03 milliliters. Then we keep food uptake constant and interpret egg production. So for every unit increment, for every egg produced, an extra egg produced, water uptake decreases by minus 3.257. So you can see that when the birds produce eggs, they are not taking in water, that much water. So after they produce eggs and then they are eating food, the water uptake increases by 3.0307 milliliters for every gram of food taken in. Now, because we have more than one independent variable, we will use R squared adjust to check the amount of variability explained in the response. So if we look at the output, the R squared adjust is 0.9521. And this indicates that 95.21% of the variability in water uptake has been explained by the regression model. And because the p-value is small, you can see the p-value, overall p-value is 4.677. It indicates that overall, there is a significant linear relationship between water uptake, food, and egg production. But if you look at the coefficients, and we look at food uptake, it is very significant, indicating there's a linear relationship between water uptake and food uptake. Now, when we go to egg production, the p-value is 0.33. It is greater than 0.05. So meaning we have no evidence to reject the null and conclude that there is no significant linear relationship between water uptake and egg production. So when a p-value is non-significant, it means, it does not necessarily mean that actually there's no linear relationship. But what the program is telling us that the existing relationship is not statistically significant. Maybe because the values are very few, maybe we need to go and collect more data, or we need to model the data differently. Okay, so that is multiple regression. So you can go ahead and test the residuals just like we did before. So let's go back to, I'm going to clear this and go back to the R Studio. And you can add confidence intervals, all that. Then you can also construct a plot if you really want to construct the plot. Okay. So what we are going to do is we want to deal with the categorical variables in these 45 minutes left. And also let's look at dummy variables and also look at polynomial regression. So before I go there, any question in the chat? What kind of analysis we use when there is a zero outcome in a 2x2 table? That is categorical. If there's a zero and you're using chi-square will complain automatically that the analysis is not valid because the expected count is 0. So if you have those zeros there, you remember you can transform your data, as I mentioned, or you can use the log linear model. Okay. Any question? And my colleague Helen will be explaining more about that. Any question? Should we continue with the categorical variables? What? Thomas, answer that. Okay, if you want to check interactions, when we introduce our categorical variables, then we can now check our interactions between the given independent variables, which are continuous, and our categorical variables. Okay. Otherwise, we can check also interactions and analysis of variance, as my colleague will be explaining after me. Okay, let's go and do the indicator variable. Okay. So we are going to read in our data is called uptake. So let's read in that data. Sorry. So let me just look at this. I want us to look at the data and I show you the categorical variable. So this data is about uptake of carbon dioxide by plants, 2 species, Pinus C and Pinus P, and then time taken for the plants to take in the carbon dioxide is our independent variable. So uptake of carbon dioxide is the response, time is the independent variable, and species is also independent but categorical. So if we have such a data set, the first thing we do, we can do a plot to see what sort of data we have. So probably we can just construct a plot. Okay, so let's go to the RStudio. So I just want us to see a plot on, or to avoid confusion, let's follow the script. The second part here is we are assigning codes to the categorical variable. And we are saying uptake is the code, is the object name, uptake $species. So we are saying that our new variable is going to be species 1 in uptake, and it is equal to if else uptake $call species is equal to Pinus C, then call it 0, otherwise 1. So that is what this if sign means you give it the object name, species 1 is equal to if else species is equal to Pinus, then Pinus is going to be 0 or else 1. Then let's view. So we run line 176 and then view. So you can see that in the RStudio window, you view your new variable called species 1, and Pinus C has been labeled 00, and Pinus P has been labeled 1111. Okay, so species 1 is our dummy variable. Remember that 00 and 11 do not have really meaning. We are just coding our data. So you can close that by Xing on the menu where there is uptake. Okay, so we want to plot the data uptake as a function of time. That is line 180. So if we run, we see that if we look at the plot, let me zoom in and share. So this is our data set. You see that there are two bands or two groups. There's this group here and there's this group here. If we fit in a line across, we'll see that the line will not touch most of the points. So we want to take care of these differences in the two groups. That's why we are introducing the dummy variable to see whether we need one line to go through or we need more than one line. Okay, let me share the script. Okay, so we run line 181 and it's going to be, the object name is called mod. Linear model uptake is a function of time plus species 1 and data equals uptake. So that is our regression model, and let's run it and then get the summary of the model. Okay. Now, if you need the analysis of variance table, instead of LM, you put AOV. Okay. So instead of LM, you use AOV. Okay, so let's look at the output. So we find that when you look at the coefficients, we have the intercept, which is minus 2.84. Time is 0.202. Species 1, that was the dummy variable, is minus 1.046. Okay. After that, we look at we can interpret these values, but before we do the interpretation, let's look at the p-values. The hypothesis we are testing is that there is no linear relationship between uptake of carbon dioxide and time plus species. Okay. So then when we look at the p-values corresponding to each independent variable, we find that the p-value corresponding to time is significant at 0.05. It is less than 0.05, indicating that there is statistical evidence to reject the null hypothesis and conclude that carbon dioxide uptake is linearly related to time. When we come to our dummy variable, it has a p-value of 0.472. The p-value is big. It's bigger than 0.05, meaning there's no evidence to reject the null. So there's no significant linear relationship between uptake and species. So once the dummy variable is non-significant, that shows you that you actually don't need different models to fit on pinus C and pinus P. You can have only a model of uptake and time. Let's look at the R squared adjust. Our R squared adjust is 0.889, meaning that the amount of variability explained in uptake by the regression model is 88.9%. Okay, so if you find that actually you don't need that dummy variable in the model, then you rerun your regression analysis without the dummy variable. So that we can do easily in the output. So we can just copy this and put it down. Oops. Sorry about that. Undo. And then I'm going to call it mod 1 without the dummy variable because it was non-significant. Okay. So when I run that, the second model without species, and I ask for the summary. So let's concentrate to the console. So if you go down where we have uptake and time, we see that our R squared is 0.9065, meaning 90.65% of the variation in uptake has been explained by the regression model. Okay, then you can go ahead now and test for the residuals using the plots that we've already talked about. Okay. Okay. Any question before we go to polynomial regression? Any question before we go to polynomial regression? Let me see in the chat. Dummy variable F statistic. Dummy variable code for more than 3 variables. Okay. We say that when you have more than 2 categories, then we need 2 dummy variables, because the number of dummy variables is equal to the number of categories under each variable minus 1. So in this case, we had only 2 dummy variables. 2 categories. Minus 1, we get 1, indicating that you only need to formulate 1 dummy variable. So if we have 3 species, then we will need 2 dummy variables. So that means that in our data set here, so if I can go back to the environment window and open uptake. So we see that if you look at the RStudio window, uptake, time, and species, then our dummy variable has 0, 0, and 1. That is only 1 dummy variable. If we had another species, maybe Pinus B, then we are going to formulate the second variable, dummy variable, which is called species 2. And Pinus will be 0, 0, then Pinus 1 will be 0, 0, then Pinus B, as for Betty, will be 1, 1. Then what you do, you include all of them in the model when you're running your regression model and assess whether they are significant. In this case, the dummy variable was non-significant, so we can't really go ahead to do more analysis about it. If we found that it was significant, then we are going to actually write our regression models differently. Okay. Okay. Any other question? Let me check the chat. Okay. In the case of multiple regression, if we want to determine okay, so you want to find out which, somebody has a question that in case of multiple regression, how do we determine which independent variable has influence, more influence to the response? We run a correlation between the response and the independent variables. You remember correlation is related to the R squared. R squared, if we get the square root of R squared, it gives us the correlation value of each of those variables you've put in the model. So, in
threshold value. Did you say something about threshold value?
In case you want to see which independent variable has more influence on the response, look at the correlation. The one which is highly correlated with the response is the one which has more influence to the response compared to the other. Okay? And please put your questions in Q&A. My colleague Thomas is answering them. In case you find that you have a burning question, post it in Q&A. The Q&A is redundant and you're using the chat, yet they disappear so quickly. So please use the Q&A. Use the Q&A. What is F statistics and at what value is significant? Okay. F statistic is obtained from the F distribution table. The F distribution table can be downloaded from Google or any other website of statistics. They are at different probabilities. There's one at 10%, 5%, and 1%. So in the F distribution table, we have the numerator degrees of freedom and denominator degrees of freedom. Maybe let me try to look for one. Give me 2 minutes. I look for an F distribution table and show you how it looks. It makes life easier than me talking about it. So let me just quickly look for an F distribution table. Okay, I've gotten one here. This is an F distribution table. Hopefully it is clear. Let me make it more visible. Hey, what is happening? Okay. Okay, in this F distribution table, you can see that we have degrees of freedom in numerator, and then on the vertical, we have degrees of freedom in the denominator. Now, in our example, we have the example in the notes, we had 1 degree of freedom and 29, where 1 is the numerator and 29 is the denominator. So we can go to 1 degree of freedom, you can see it is right there. And then scroll down to 29. So apparently this goes up 7. So let's use 7. So if our denominator is 1 and the numerator is maybe 3, so you go to 1, scroll down up to 3 and look for probability. You see these values here where there is P, those are probabilities. So probability 0.05 at 1 degree of freedom and 3. The F value, the tabulated F value is 10.13. Now, if your F calculated by the R program is, for example, 50, and you're comparing it with the 10, you find that the value you've calculated is greater than the tabulated value. And that shows that there is evidence to reject the null and conclude otherwise. There is a linear relationship between volume and diameter, or between water uptake and egg production. So that's how we get the critical values from the table. This table you can download and look at the numerator degree of freedom, which is the regression degrees of freedom. The denominator degrees of freedom is the mean square degrees of freedom. So wherever they intersect at P is equal to 0.05, that is the critical value in that table. Compare it with the computed value in R. If the computed value in R is greater than the tabulated value, then reject the null hypothesis. If the computed value is less than the tabulated value, then you do not reject the null hypothesis. Okay, so I'm going to stop sharing. And we go to, then I share the script again. Okay, so we are going to look at the last bit, which is polynomial regression. So I'm just cleaning the history. I don't know what I always do and disappear. Sorry, I must have pressed some button. Okay, there we are. So we are going to do polynomial regression. Okay, so we are going to read in our data on line 189 called HAD. Now, a brief history about this data set. When we are making paper, we get the logs from the trees. We harvest the trees and chop in smaller pieces, pound them, and then make pulp. Then put some chemicals, add some chemicals to bind them together, and then process paper. So this data is from paper production. So they are looking at the hardwood pulp and the tensile strength of paper. Okay, so I want to produce paper which is hard enough to resist any damage. For example, if water splashes on the paper, will it automatically tear in 2 pieces? So they wanted to investigate what is the maximum hardwood concentration they can use to produce the best tensile strength. Okay, so let's read in this data. It is on line 189. So just click read and the data set. So that's our data set. And the third line is 191, just to show the column names so that you don't miswrite them. And because they had dots, that's why I had to read them. Then we are going to draw a plot to see whether it is linear. There's a linear relationship between tensile strength and hardwood concentration. This data set, I got it from Montgomery and Parker. Okay, so let's draw. So you can see that our plot in the plot section or on your screen shows that actually we do not have a linear relationship between tensile strength, and hardwood concentration. Now we want to fit a linear regression, but assuming that you ignore the fact that it has that type of relationship and just run a linear model. That is the first step we are doing. So when we run line 195, that's just a linear model. You run and run the summary. So let's look at the summary. If you look at the console, you see that there is a significant linear relationship between tensile strength and hardwood concentration due to the p-value, which is 0.01. It is less than 0.05. How much variability has been explained? Only 30%. And the unexplained variation is around 60%. Okay? Actually almost 70%. Meaning that there are other factors that are important in explaining tensile strength that you need to add into the model. So it's not really a very good model. So let's go and see. Let's model that. Let's look at the plots, the residual plots. In case you use a wrong model, what happens to the residual plots? So let's run the line 198 and 199. Okay, so we have our plots. Let me zoom in. And I want to share the zoomed in plot. Oh. Okay. My zoom in plot is zoom in. Okay, let's look at the plot the way it is, because I'm trying to zoom in and it's not accepting. Probably I have another plot open. Okay, so if you look at the residual plots on your screen, the residuals versus fitted value shows us that the residuals are increasing with fitted values, indicating that there's no constant variance. When we look at the normal probability plot, small as they are, the values are not falling on the blue line. We have non-normality there. And when we look at the residuals versus leverage, which shows that there are outliers or some values which have high residuals, they are not really visible enough. We don't see anything that is so peculiar. So generally, when you look at the residuals versus fit, it's also telling us that actually our data, the linear model does not fit our data. And you see the red line drawn is a curve in the model. So what we are going to do is let's now run the correct model. So line 202 is we want to introduce a quadratic term, a new variable with a quadratic term in our data set. So you write hardwood and call it a new name. And then we are squaring the initial hardwood concentration. That is line 202. So there we go and view our data. So if you view our data, we've formulated a new variable called hardwood con, which is when you square 1, you get 1. When you square 1.5, you get 2.25. So we've introduced a quadratic term onto the hardwood concentration. So let's now run a regression equation. Okay, so let's run. It's called, the object name is model 2, linear association between tensile strength, hardwood concentration, and then hardwood squared. So we run our model and run. So now let's concentrate on the console. And the console is showing us that there's a significant linear relationship between tensile strength and hardwood, and as well as tensile strength and hardwood concentration squared. You can see the p-values are all smaller than 0.05. If we look at R squared adjust, you remember that the other time our amount of variability explained was just 30%. But in this case, the amount of variability explained is 89.7%, indicating that the variability explained in tensile strength by the model has actually improved by 50%. So indicating that now we have a better model using R squared adjust criteria. So let's look at the plots. How have the plots improved? So when you go to line 208, we instruct the program to arrange our window in a 2x2 and then draw our plots. So I'm going to try and zoom in again and see whether I can get these plots. Let me try. Okay, I'm going to stop sharing first. I want to see why I can't zoom in. Let me stop this one. And then go back. Okay. Hopefully now I'll be able to zoom in. Apparently it has refused. Maybe. Let me see, close up one. Give me 1 minute, please. I close up this. I think there is.
What is this one?
This is R.
No, this you need to close here.
Okay, then let's now go and
Zoom and see.
zoom. Okay. Okay, so let me share. Sorry about the short interlude. So these are the residual plots for our model with a quadratic term. And you can see that now it's a random scatter of points compared to the one we had, where it was showing that the linear model doesn't suit the data and the residuals were increasing with fitted values. Then when we look at the normal probability plot, not very good though, but most of the values are not very far from the dotted line. If we look at the residuals versus leverage, we find that there is 1 point here below the red dotted line. And that point indicates that it might be an outlier. It has a higher residual. So you don't delete immediately. Go and investigate whether it is a typo. or it is a genuine residual. If it's a genuine residual, we say that we analyze our data with the residual, look at the parameters, then analyze the data without the residuals, also look at the parameters. If you see that there's a significant either decrease or increase in the magnitude of the parameters, then we consider removing the residue. Okay. So that is the polynomial regression. Probably we can add even a quadratic term if you want, but you can do that in your free time. We can try to add a quadratic term and see whether the model improves even further. But if we've already explained 89%, then most of the variability has been explained in tensile strength. And remember that when we are doing regression, we are doing model building. We do not need a complicated model. A complicated model is difficult to interpret and it is expensive in terms of data collection. That means you're going to collect more variables than a simple model. So if you have a simple model explaining above 70% of the variation in the response, then that model is really good. Okay. Okay, so I'll stop sharing this. And close. I'll first of all close this plot just in case we have anything. So the rest is just graph off to remove the graphs, or you can use the brush. And I want to give an opportunity. I want to give you a break of 8 minutes. Then we will start at 12. Dr. Thomas is coming in to talk about analysis of variance. If you guys can finish analysis of variance today, in the morning, I'll request for 30 minutes to do model building with you people. I'll request for 30 minutes from my colleague, Helen, and we do model building. Model building is where you have so many variables. You've collected so many variables, you don't know which one to include in the model. And then you do model building or variable selection. Other people call it model building. Other authors call it variable selection. So it's also so interesting and so real that is what actually is happening in nature. In nature, we do not have simple linear regression models. We have models with so many variables in them, okay? So I would like to stop here and give you these 7 minutes to have a break. And in case there's any question in the Q&A or the chat, I'll answer them. So when you come back from the break, you find the answers there. So can you please go for a break? And I would like to thank you so much for being such good participants, excellent participants. He's saying squaring the data, does it help? Yes, it helps. It's one way of transforming your data. Okay. Thank you so much. You've been so excellent. I haven't had a problem with you. So you're excellent participants, and I would love to come to your universities and teach you face to face. Thank you so much. Okay, so let me give you a break. Please go for the break so that you can refresh, stretch yourselves, and then you come back. We start with Dr. Thomas. He's coming in with ANOVA for experimental design. Okay, thank you so much. Okay, you're welcome. Thank you, Mohammed. I'll come to Sudan soon. Okay.
Hello, everybody. Are we back? Is the sound there now? Okay. Good. Yeah, so we're going to briefly look at analysis of variance. I did the analysis of the data first. So I'm going to just show what I've done, and then later we can run together. But after explaining, even on your own, you can run. So I'm going to start by first explaining the data set that we are going to use. Is kind of well, it's one of my favorite data set, but I decided to tweak it a little bit and change. So we are going to look at a data set from a Latin square design experiment, where the interest is to test the effects of feeds. There are 5 feeds on milk yield. So remember, in Latin square, if there are 5 treatments, that means we need 5 rows and we need 5 columns. So we are going to have, we have 2 blocking factor. We are going to block using animal. We believe that each animal has some uniqueness and there is differences as you move from one animal to the other. And then the second one, we also block using the milkman. We also think each milkman could have some uniqueness that may affect the outcome of your study. So I have this is how the experiment could look like. So in week 1, the animal number 1 is this animal with beautiful long horns. So week 1, okay, when it is milk by, we have milk. The sound is not clear. Is my sound okay? Yeah, I think it's clear. So probably there could be somebody. Okay. Okay, so we have this animal here. And then milkman 1 gave us when it is treatment A, and the milk by milkman 1, we got at a 3.8. The same animal when it received treatment B, with milkman number 2, milk number 3 and 4. So this is a perfect, what we call a Latin square design. We have, these are our row number 1 is related to animal 1, row number 2, animal 2, row number 3, animal 3, row number 4, row number 5. And then the column is milkman 1, milkman 2, milkman 3, milkman 4, milkman 5. So that is the data that we have. So what we need to do, somebody asked the question the other day that how do we enter this kind of data in Excel before we do the analysis. So what we could do, we could look at, let's say we could look at a cow. I mean, that could be one way of looking at it, our cow. And then we look at milkman. And then we could look at milk yield. So we have 3 different columns. So here we have cow number 1. We also need treatment rather. So we need treatment. Okay, let me first wrap a bit of this. Okay, so here we'll have our cow. And then we have the milkman. Let me put it as MM. And then we have our treatment, which is our feed. Let's call it F. And then we have our milk yield. So remember, the milk yield is our variable that we are interested in. So here we can have cow number 1, milkman number 1, treatment A, and then the value here is that. So the value here is 33.8. And then we go to cow 1, milkman number 2, treatment B, a value of 33.7. And then we can go on milkman one, cow 1, milkman number 3, and the treatment is D. And then we go for 1, milkman number 4, the cow, the treatment is C. And then we go for 1, 5, the treatment is E. And then of course you have your values, your different values there. So this is what we have in our data set that we want to analyze. So the first thing that we are going to do, we are going to look at our. So this is our. So the first thing we are going to do, we are going to look at some summary statistics for this. Remember, we say before you go into and do your inferential statistics, the first thing that you need to do is to do what Susan did yesterday and try to do some exploratory data analysis. So we're going to move to the next one and say, well, let's just do some simple plot. So we look at the milk yield for the different feeds. So you can see here, this is a box plot. So for feed A, the mean is about 37. For feed B, the mean is this. For feed C, feed D, and feed E. So you can see from here that based on the value here, based on the median, we seem to be having a problem with feed C. It seems to reduce the yield substantially. Here, if we look at this, we seem to have apparently no difference between feed A, B, C, and D, but feed E seems to stand on its own alone. But we also can see that in addition to having a low yield, there is also a lot more variability within, there's a lot more variability in for E. So you see, if we look at this is all variability. There's a lot more variability here compared to the rest. So you see, there's the lowest variability is in milk for feed B, and then feed A, followed by, okay, these two are similar. So that is what we can see from if we look at the summary for the different feeds. So remember, when you're looking at the summary for the different feed, if we are looking at here, for example, we are not taking into consideration the cow, we are not taking into consideration the milkman, we're just looking at all the information relating to that particular feed. We can also come and do the same thing for the cows. So you can see that this is our cow number 1, number 2, number 3, number 4, number 5. So you can see that there seems to be, I think the cow with the lowest amount of milk is this one here, followed by these two, and then these two seems to, cow number 4, number 5 seems to have the highest amount of milk, but they also seems to have higher variability. So if you go back and look at our cows, yeah, we could say, well, I think these cows are okay. So cow number 2 seems to be the one, okay. So we can see cow number 1 with a lot more variation. This cow number 2 and number 3 seems to have less variation, but then there also seems to be, you see now, although the mean for cow 1 is up to around, the median is around 33, there is the one of the value is actually almost 25. So there's also an outlier there, there's an outlier there, there's some outlier there, and some outlier there. So you probably be asking yourself already, what could be the cause of the outlier? Could the cause of the outlier be the milkman? So when we come here, we try to look at for the different milkmen. So here you can see milkman number 4 seems to have a lot of variability in the milk whenever they do the milking. There seems to be a lot of variability. So milkman number 5 seems to have less variability, but there seems to be one particular value that seems to be extremely low. So this value here for milkman number 5, it looks like could be the value responsible from cow number 1. But these are the things that you need then to start looking at and say, okay, could this be an outlier or what? If I ask the question now, if you are the farm, if this is your animal, which milkman do you think will be stealing your milk? Can I see in the chat? Some will say you're wondering what the role of the milkman is in the experiment. Well, I mean, at the end of the day, when you're doing an experiment, a milkman should, somebody needs to milk the animal. So what we are saying is that if the cow cannot be milked by one person, you're going to have several people milking your cow. Now, a milkman could introduce a source of variability into our taking, and that's why we need to take it into consideration. Okay, so I can see somebody say milkman number 4, somebody say milkman number 5. So can you give reason as to why you think it is number 4? So you could be having your own reason as to why a particular milkman is you consider to be having what you consider to be. So would you consider, okay, so those who say milkman number 4, what are the reasons as to why milkman number 4, he could be the one stealing your, okay, somebody say yes, because the yield is very variable. So in a way, if you're looking at the yield today is like that, the yield is in another day. Well, variability could also be okay. Yeah, that could be one thing. Okay, and milkman number 5, those who say milkman number 5, why do you think so? Say milkman number 3, the yield is low, okay? Yield is low compared to other, okay. So at the end of the day, if that is the information that you've got, you're supposed to interpret that information based on your knowledge of the subject matter. Okay, so we have done this. We could also go and look at, we can still explore. So here we can see, for example, that feed E produces the least amount of milk. The differences exist among the cows. So this could affect our comparison. If we ignore the cows, it could actually affect our comparison. So remember, there is a cow with this amount of milk, and then there's one with this high amount of milk here. So there seems to be no differences between the milkmen. Okay, so at the end of the day, we could actually say, well, we don't need to care about the milkmen. We can actually remove it from our model. But at the end of the day, this is what is coming out of our exploratory data analysis. Okay, so let's move to the next. So here we can also look at the feed for the different, for milkman 1, for example, you can see that as you move from feed A, B, C, D, we seem to see this pattern here. And then, of course, E is, from milkman 1, E is the lowest. For go to milkman 2, E is also the lowest. You go to milkman number 4, E is the lowest. Number 5, E is the lowest. Now, but there seems to be something going on milkman number 3. E is actually not the lowest. So you can see here. So the question one would ask here, for example, was there a switch in the value, in these two values? Possibly. Okay, so this is where you need now to start looking at and start saying, okay, maybe we check whether there is actually, this could be a source of error. Okay, or what could have happened in that particular day for this particular milkman. Now you can also look at this for the different cows. So you can see cow 1, E was still the lowest. For cow 2, E was also the lowest. For cow 3, E was the lowest. For cow E was the lowest here. And then E was also the lowest there. So certainly a question mark can be asked here. That something must be going on here. How comes only this milkman, okay, seems to have a difference between C, E, A, D, and E? Okay, So we have done our exploratory data analysis. So we probably can tell that, well, we may actually, the feed is actually somehow important in explaining the variability, but that important could only be, could probably be attributed to feed E. The rest seems to be similar. And then you see from here that, well, the effect of the cow is certainly there and should also be in our model, but here probably the effect may not be in the model. So, but we will see exactly what is going on. Okay. So now the next thing now that we need to do, then we need to do analysis of variance. Now, what we always do in data analysis is we have what we call a statistical model. Now, with a statistical model, your statistical model is trying to explain the variation that we observe. So you can see from here that there is actually a lot of variation in milk. The question is then, how can we explain this variation? We need to look at the issue of the design. How was the study design? So the design in this case, where we have our the cows are different, so that could be a possibility of affecting our model. We also see that the milkman is different, so could also be a possibility of affecting our model. And then the treatment here, we have the different feeds that could also affect our model. And then, of course, the random error we're talking about, if we account for every other thing, whatever remains is what we call our random error. That is our noise. So this model of ours here is trying to explain this variation here. How come this value here is different from that value, is different from that value, is different from that value, is different from that value? And we're saying the difference could be because of the design of the study where we had different cows and we have different milkmen. This could have contributed to the variation, but it would also be because we have the different treatments. But even if we had the same treatment, same milkman, milk several times, we could also still have variation, and that variation is captured and that, okay? Are we together? I mean, seeing in the chat what is going on. Are we together? Yes. Okay, good. Okay. So the next thing then, okay, we now can fit very many models here. So we can fit what we call them a full model. A full model here is our Latin square model, where we have the design effect. So the two design effects is the effect of the feed. The effect of the feed is our treatment. The effect of the cow, the effect of the milkman are part of our design. And then, of course, we have the random error. So this is our full model. So we are looking at our milk yield being explained by the effect of the feed that the animal received, the effect of the cow, and then the effect of the milkman. And then anything else that we cannot explain, it will become part of our error. Okay. Of course, then at the other extreme, we have what we call the null model. So with the null model, we have no effect completely. There's no design effect. There is no treatment effect. So what we are saying that there's no differences between the animals. There's no differences between the milkmen. There's no differences between the feed. So what we have is that the general population mean and everything else that vary is our error. And between these two models, we have three other models that we are going to look at. So what we have here is we have sometimes there's what we call a nested model, where one model is a subset of the other. So let me see what is in the Q&A. No material has been provided. Please check check the link. Okay. Okay, so we have this. So what we are going to do now, we are going to look at the different models, and then we are going to see the effect. So remember, what always happens is that as the amount of variability in our data set remain the same. It doesn't change, but the proportion that is explained by the different factors changes depending on the model that we have. If we have a null model, that means everything else is going to be error. Okay, so let's look at the other model. So the first model that we talked about is our null model, which has the general mean, and then it has the error term. So in this case, this is going, everything, all the variability that we have is going to go to the error. Okay, then the other model that we can also consider would be to just look at the treatment effect. And we say, well, there is no effect of the cow, and there's no effect of the milkman. So in this case, we can cross this one off. We assume there is no, the cow, we could assume the cows are the same, the milkmen are the same. And then what we have here, we have randomized complete block design without any blocking. And we assume now that this is our CRD. So we can also fit analysis of variance for CRD, and then we assume that everything else apart from the treatment effect would be here. Now from model 1 and 2, which one will have a bigger error? Can I see in the chart, model 1 and 2, which one will have a bigger error? One, okay? Okay, model 1 will have a bigger error because everything else is actually lumped together. Good. Okay. Then the other thing that we could do is we could go for alternative number 3. With alternative number 3, we could assume that we are running a randomized complete block design with the cow effect as a blocking factor. So we assume this one doesn't exist. So we just assume that a cow is a blocking factor. So this is our block number 1. This is our block number 2. This is our block number 3. This is our block number 4. And this is our block number 5. So this is randomized complete block design with the cow as a block. Okay, that is our model number 3. So here you can see we still have the feed effect. We have the feed effect. But here now, we have error. So part of the error comes here. Part of it is taken away by that. While here, where part of the error is there, and then part of the error is there. Okay, so that's why now the error, this is the bigger error, followed by that, and so on and so forth. Okay, so here we have the cow effect. So we assume that this doesn't exist, and we have randomized complete block design. Then our model number 4, which I'm still going to wrap up, we assume now that the feed effect is there, but the milkman and the milkman effect is there. We ignore the cow effect. So we assume that the cows are all the same. Okay, so then we have, this is our model. This is our block number 1. This is our block number 2. This is our block number 3. This is our block number 4. This is our block number 5. Okay, and so on and so forth. So in this case, then we assume that, okay, we can ignore the cow effect, and then we can see. Then of course, the full model where we consider everything to be in the model, and whatever we cannot explain now becomes part of the error. So you can see from here clearly that when we go to do our analysis of variance, the error term should be reducing as we move this way. Okay, but I mean, it's not a guarantee that if you put in a blocking factor, you're going to benefit. So you may actually block and you still find out that you could be having a bigger error than without blocking. So we are going to look at the different scenario that's there, and then we can see. So let me see. Yesterday has been shared twice. No, please check within that. They just update the file and they should be inside. What is the difference between fixed and random? Please, we are not going to talk about that now, later. Keep your question, I'll talk about it later. If I don't answer today, you ask me tomorrow. Okay, we are going to look at the assumptions of the complete model. Okay, good. So let's move to the next slide. Okay, so the first thing, we're going to fit a null model. With the null model, you can see everything is just the residual. So this is the sums of squares, which actually estimate the total variability in our data set, and everything here is considered to be noise. The mean sums of squares is this time we can take this our sigma square, which is the variance. And then, of course, so here we can see that for the null model, our residual mean sums of square, which is our variance, is 12.36. That's our noise. If we fit a randomized CRD model, we ignore the effect of the cow and effect of the milkman. We assume those ones don't exist. These ones are all the same. Then we only compare our treatment. So this would be our residual. So we can compare. So as we indicated above, you can see that when you introduce the treatment effect, we are going to remove part of the variability here. So part of this sums of squares goes for feed, and part of the sums of squares now goes for residual. So these two, if you add these two, you should get that. Of course, the effect is now onto the mean sums of square. So you can see we are able to reduce our variance from 12.36 to 7.038. But something else is also happening here. You see from here, the degrees of freedom for the residual is 24. Okay, but here the degrees of freedom of residual is 20. So the other degrees of freedom has actually shifted here. Okay, and remember, the degrees of freedom of the residual can actually be considered as a measure of efficiency of your experiment. The higher, or the measure of precision, the higher the degrees of freedom, the more efficient your experiment is. So what is happening here is that by introducing a factor into our model, we actually reducing on the degrees of freedom, but we also kind of help to reduce the noise by dividing this into two components. See, this part now is known, so we separate it from here. We consider all this to be unknown. Okay. So this is our second model, which we ignore the cow and milkman effect. We only look at the effect of the treatment. I kindly request to the materials have been shared. Please, can somebody reshare the link can somebody share the link in the chat, please? Okay. Okay. So we have two models here, model 1 and model 2, and we see that there is an advantage in introducing the effect of the treatment. So the next thing that we are going to do is we are going to go to model 3. I'm going to leave this one here so that I can compare it with model number 3. So when you go to model number 3 now, we bring in the cow as a block. So here we have feed. So remember here, our sums of square for the feed and degrees of freedom for the feed has remained the same. Okay. But we also have now a sums of squares for the cow, and this was taken out of this. Remember here we had 140.76. Here now we only have 53.363. So by introducing the cow into our model, we actually change our residual from 7 to 3.33. We change it by more than half. So you can see now that our model is improving because we're having less and noise in our experiment. So let's go and look at model number 4. So model number 4, it uses the milkman as a blocking effect. So here we ignore the effect of the cows. We only look at the milkman and then the treatment. Something strange is happening here. See, this is a model as CRD. This is a model as RCBD with the milkman as a block. We actually lost here. There's a big loss here. You see now the noise has actually increased. And this is why you should be careful. Blocking does not necessarily mean that you might benefit. Why we seems not to benefit from here is that we are losing our degrees of freedom here. Okay? You see our degrees of freedom here now has moved to 16 because we have taken 4 and given it to the milkman. And the milkman is not contributing enough to reducing this. You see the sums of square for the milkman is very small. So we lost our 4 degrees of freedom and we are gaining very little. That is why at the end of the day, we have this. But we should also be able to check when we come to checking our model, we should also be able to check and see whether there is any sign from our model that our model is not good enough for the data. Why we reduce the sums of squares, the mean sums? We are reducing the residual sums of squares because we are adding more explanatory variable in our model. So instead of assuming that everything is not known, we actually adding a lot more info. We are picking from the noise. So now we have less and less noise, and that is good for our model because that shows that our model is efficient. And if you are to calculate the R square for this model, it will be higher than if you are not removed the noise from the model. Okay. Okoro Robinson Mary said, greetings, I joined the class today. Can I please have the benefit to join the chat group? You're already in the chat group. Somebody was creating a Telegram group for the chat. Can you please share the link so that Mary can join? And also it would be good to keep that group there because if there's any information that we will share, we would also want to, we can track you and follow you up. If there are some studies that we want to carry out or there's some courses that we want to do, we can always follow you up on that. So please share the link. And also at some point we may want to join the group so that we can follow the discussion going on. Okay, so we can now go to our model number 5. So from here, we gain. When we move from here to here, we gain. When we move from here to here, we gain. But when we change, we move slightly in a different direction. When we move from here to here, we actually lost. You see, there was a gain here. From here to here, there was a gain. From here to here, there was a gain, but we actually made a loss. So let's now go and look at our Latin square, the full model. So here then we have, it looks like I repeated the same thing. Okay, so here now we have the model with both factors in. So you see now there is feed in, it takes 4 degrees of freedom. There's a cow in, takes 4 degrees of freedom. There's milkman in, it takes 4 degrees of freedom. So here now we have, this is our residual, okay? So now if we look here, of course, the final model, the Latin square model seems to be the best model in terms of the noise, but then the difference between this model here and the cow model is apparently very small. So one would want to ask whether, do we need this very complicated model with the cow and milkman? For this case, it is yes, because that was the design of the study. But if you are to repeat the same study again, you would say, well, I don't actually need to take the milkman into consideration when I'm designing my study. So you can see from here that we are able to show that the different factors that we put in the model, how they improve our model. And then we also able to see the losses that we can actually make if we go ahead and do our randomization. And go ahead and assume a wrong design, you actually make some losses. Okay, so let's, any question? Are we still okay? Can I see in the chat whether we are still following well? Acheng is asking for PowerPoint. It has been shared, please. The link, somebody could put the link back. Okay. So now we have our models here. Maybe what we can do, let me try to interpret this model here now before we go to look at the assumptions of the analysis of variance. Okay. So here then, let's assume now that we are going to take our model number 5. This is the model that we are going to take as our model for the interpretation. Okay. So here, you have the degrees of freedom, you have the sums of squares, you have the mean sums of squares, then you have the F value. Now, somebody was asking that why F statistics or why F test? So this is now the ratio of our noise here to a signal, okay? So this value here, to get 12.7, we divide this value 38.974 with 3.067. So we get this value here. Now from our normal statistic class, we always say this is our F value, which is calculated. We compare with the F value from the table, and then we declare, we reject the null hypothesis. Now, of course, the most, when you're doing analysis on the computer, the concentration is always on the F and F on the probability here. So here you can see that the probability is 0.00284. Here you have 0.003533. And then here you have 0.3 that. So our null hypothesis, H0, in this case, our null hypothesis, what we're saying is that for the feed, we're saying that the mean of feed A is the same as the mean for feed B is the same as the mean for feed C, the same as the mean for feed D, and the same as the mean for feed E. That is our null hypothesis. And then the alternative hypothesis here, which is HA. So here we say at least a pair of these treatments are significantly different from each other. At least a pair of the treatments are significantly different. We only need one pair to be significantly different for us to declare to reject the null hypothesis. So here, in this case, our p-value is less than, say, 0.005. So if we are set our significant level alpha to be 0.05, you can see from here that our p-value is less than 0.05. So that means we are going to reject the null hypothesis and declare that at least a pair of this treatment here are significantly different from each other. We go and do the same thing for the case of the cows. So we can see here that our p-value here is less than 0.05. And that implies that we reject the null hypothesis that the means of the cows are the same. So we say at least one of these cows performs significantly different from the other as far as the milk yield is concerned. And then when you look at the milkman, we seem to see that the value here is greater than 0.05. So that means there is apparently no significant differences between the different milkmen used in this study. So we don't need to worry about correcting for their effect when you're doing the analysis, or next time when we are doing our analysis, next time when we are designing another study, we don't need to worry about the milkman as a factor in our study because it seems not to have effect on our model. Let me check. What is the minimum error acceptable? Please, there is no minimum error acceptable in ANOVA. Okay, so if there are issues that we have, if you have only three, what do we compare them? We are going to look at the comparison with the treatment later on. For now, We have rejected the null hypothesis. We are saying at least a pair of treatments are significantly different from each other. So what we are going to do later on, we are going to say, okay, if we agree now that this analysis of variance result stands, so what the next thing we are going to do would be then say, okay, which of the pairs of treatment are significantly different? So in that case, we are going to go there. Mideka, we are going to, if we have time, we're going to look at the minimum number of replication, but like what Susan yesterday talked about, what she talked about in, not Susan, Ellen, when you talk about the number of the sample size, the similar argument is also brought in here for the number of replication in the study. So your question, I think, is taken care of in the chart. What is the degrees of freedom? The degrees of freedom in this case is more to do with how much information you have from a given source of variation. So it's more related to amount of information that's available. So because here you have 5 groups. So if you are estimating, you want to estimate or you want to look at the effect of the group, you only need to look at 4 effects. The 5th one will automatically set in. It's like if you have 5 chairs, you have 5 people to sit on the chair. The first person has the 4 degrees of freedom, can sit in 4 different places. The second one can sit in 3 different places. So that will be, you reduce the degrees of freedom. But the 5th person now has no option but to sit in the remaining one. So that is our issue of the degrees of freedom. Okay, let's continue a little bit. Okay, so we have this, and then later we'll say, well, we agree now that, remember, we're not interested in comparing the cows. We want to remove the effect of the cows from our interest is comparing the different feeds. The cow was part of the design. We're not interested in comparing the milkman, but we thought the milkman would introduce the noise in our experiment and will prevent us from detecting the differences between the treatment that we are trying to compare. Okay. Now, when we're coming to the assumptions of analysis of variance, of course, I talked about our different models that I talk about. So we talked about a CRD model. So a CRD model, you have the general mean, you have the effect of the treatment, and anything else will be considered as our error. Then for RCBD, part of the error now can be broken out, become part of the block. We saw 2 different types of RCBD. And then for Latin square, you'll have your error here, part of it will now be into an extra block that comes in. So you have this. So in this case, you also expect that the residual will reduce as you move along the way, down as you change the model. Now, of course, in statistics, when we are talking about assumptions, we are always very much interested in what we call the error term. So the error term is the difference between the value that you have observed and what your model will estimate or will predict. Okay, so if you observe a value of 30 and your model said, well, the value should be 29, so the difference between these is 1. So when we're looking at the analysis of variance, we are trying to look at the different assumptions of analysis of variance. We are very much interested in this, what we call the error term. The error terms are the one that we looked at. Why is the error term? Because we assume now that if the design and then the treatment components have been removed from your model, the error term is supposed to be noise. So a noise should behave in a certain way. If your noise shows pattern, then that means there's still something in your noise that needs to be removed. Okay. So at the end of the day, we are going to fit our model. A model will suggest for us some value, and then we also have the value that we have observed. So let's say, for example, I have a model that can predict the amount of money in your pocket. So I have a model, I can look at you and I can tell you how much you have in your money. So if I get participant number 1, participant number 2, participant number 2, number 3. My model tells you that you have, say, 5,000 in your pocket. And actually, you have 0 in your pocket. So the difference here is actually very big. That means my model is not very good as far as predicting what is in your pocket is concerned. Now, if my model can actually be terrible, especially if, for example, it underestimates the amount of money in the pocket of the male and then overestimate the amount of money in the pocket of the female. So that means there is something in my model that still needs to be removed. So we are going to look at we study the residual. The residual is the main thing that we need to study. Somebody said, when do we have an interaction effect? Is it not possible that a milkman and specific cows interact? Well, that is one of the assumptions of analysis of variance is that the effect of the treatment and the effect of the block there should be no interaction between that. So in this case, we can assume that there is no interaction between those factors. What we can do, we just want to remove the effect. So you may also need to check, actually, there could be that possibility. Okay, good question from anonymous attendee. Okay, so here, in our CRD model, we have the milk being influenced by the effect of the treatment and then by the error. So this the general mean is there also, like what? So this one here, this part here, in statistics, we always give it a heart. It puts on a heart. Okay, so this is the II. Okay, so you can see from here that Y. So in this case, we are saying from feed I, and then feed, and from feed I, and from cow J, we have this. We have Y I plus E. Okay. So that means your Yij minus a Yij at. I don't know why people decide to give a hat to this person here. Okay, we have the J there, should be equal to your residual. And we assume that the residual is noise. So a noise should have no pattern. That is one of the clear assumption here. So once we fit our model here, so this is the command that you have with you already. So model 1, you have AOV. You can also use the LM. So this is the milk yield. We're explaining it by feed. The data that we have is a Latin square. So this is the analysis of variance table that comes out of it. So here we can assume, here we say, oh, there's a significant effect of the treatment, okay? And then R goes ahead and gives you at what level it considered the significance. So it gives you at 0.001, okay? So if we look at that, the different data point I tried to generate, there are 25 data points here. I remember the first observed milk yield was 33.3. The fitted model will tell us that it's 35.75, and the difference here is negative. Okay, that means the negative means that the fitted value, the model overestimates the amount of yield in the first for the first treatment in the first row and first column, and then the same one also for that one there. The same one for that one there. So you can see actually the first 5 are all negative. That means our model overestimates the amount of yield that the animals will get. Then number 6 is positive. That means it underestimates the value. So that's what. So these are the values. Finally, when we are looking at the assumptions of analysis of variance, these are the values that we are actually going to consider in our analysis. So what you can do is, after you've run your model, remember our model is called model 1. you put a dollar sign, you can actually extract the residual from it. You can also use something like model. Model 1, if you put a dollar sign and you put fitted, then you get the fitted value. The fitted value is this one here, and then the residual is that one there. Of course, you can get this one from your data, which is the observed value. So that is where the assumption is mainly on this last column here. Okay, so the first thing that you want to do is you can get an histogram of this. You plot an histogram. You can also put a normal distribution curve on top of it. And then from here, well, you say, well, remember this is supposed to be normal. The residual is supposed to have a normal distribution. So this looks like a good normal distribution with a mean of 0, which is 0 is in the middle. And then it has some kind of a constant variance. That is the assumption that we need to make. I think Susan talked about this. So this will look at, this will test whether we have a normal distribution. The same thing is also here. This is what we call a QQ plot. So a QQ plot will test whether there is. So in this case, we can assume that in our model, the residual actually has a normal distribution with the mean of 0 and with some variance. So that one, we don't have any problem with it. But we may also be interested in say, okay, let's try to relate our residual back to the cows and back to the milkmen and actually see whether there's a particular milkman who seems to, I mean, the model overestimates the value for a particular milkman. It could also mean that that could be the milkman stealing our milk or something else, okay? Okay, so now what we're going to do now, we are going to look at this residual here, but we're going to draw a box plot for the different residuals. So you can see from here that you see now feed A had the lowest amount of milk, but it also had the highest variability. And this is also reflected in the residual. And then you also have, but as you can see, the 0 is in the middle. So we seems to be having some kind, there's some issue here that this one seems to be high. There's a lot of variability, more variability in E and say D compared to variability in the other. And remember, one of the assumptions of analysis of variance is that the error term is supposed to have constant variance. So the variance in each group should actually be constant. So we can see from here that the issue of constant variance seems to be the issue that may actually affect our model. The next thing that we're going to do, we also look at how can we look at this for the different cow. So let's see here. You see our first 2 cows. The residual for the first 2 cows are all negative. So what does it mean? That means for the first 2 cows, our model seems to overestimate the amount of milk. And then for the last 2 cows, it seems to underestimate the amount of milk. Now remember, residual is supposed to have no pattern. Residual is supposed to be random. So what this one tells us is that our model actually does not fit the data very well. So you can see what we call lack of fit here. So we have lack of fit. So that means maybe if we bring cows into our model, we may be able to see an improvement into that. Now, when we come and look at the milkman, well, we seems to be having, there's no overestimation or underestimation per se. We just seems to have variability that is actually different. So from here, I can actually tell that I think our model seems to have a problem as far as estimating the milk of the different cows is concerned. And this could mean we need to include the cow into our model. That literally would be the thing that we need. So error terms are supposed to be randomly, independently, and as a constant variance. So the issue of constant variance seems to be an issue. The issue of independence is certainly affected here. You can see that your residual depends on the cow. For cow 1 and 2, your residuals are negative. For cow 4 and 5, your residuals are positive. And then even for cow 3 seems to be actually positive, okay? So now we can change the model a little bit and bring in the cow effect. So that was our model number 3 rather. So after we've done we get this and we plot. So you can see for the feed, well, we seems to be having the same issue, although it has reduced a little bit. Now see here, at least we don't have this situation here. Can you see now that our first everything seems to be above and below? So the lack of fit that we have seen when we did not include a cow in our model seems to have actually gone away. But it seems to have also brought the problem now. Milkman number 5 now seems to be having a negative value. So the model overestimates the amount of yield. So probably milkman number 5 is the thief who has been stealing our milk according to the model that we have here. Now, when it comes to the normality, well, we seems to be having a little bit of an issue, but this should be fine enough. I mean, we need a straight line passing through. So this is okay, I think. And one of the things is that the normality assumption is not really that much of a big problem as far as analysis of variance is concerned. What needs to concern us is whether we have a constant variance or not. Okay, when we bring in the effect of the cow and the milkman, of course, if we remove our cow from the model, you can see we are back to square one. Okay, so in terms of the effect of the cow needs to be in our model because it seems to have strong effect on the model. For the milkman, we seems to be okay, and then we seems to still have the high variability here, and then the high variability here, and that may pose us a little bit of a problem. The reason why variability is that you cannot compare a group where there's less noise with a group with a lot of noise. That means you're going to get yourself into problem. And that's why assumption is made about equal variances. Okay, so the next one, if we now fit our full model, with the effect of everything. So, well, we seems to, the issue, as far as we are concerned, the variance now, there is lack of fit has actually been removed. So you can see this one is spread nicely above and below the 0. This is also spread nicely above and below the 0. This one also above and below the 0. What seems to be a problem seems to be a lot more variability in this group here, and then there's a lot of variability in E and a lot of variability in B. These are the things that probably needs our concern. The normality is fairly okay. We draw a straight line. It's not that bad. We can do with that. So the error terms need randomly, independently, and normally distributed with the constant variance. Okay. So the other way we can do testing whether the variance are constant we do what we call the Shapiro test. So here we set up the same kind of interpretation like before, is the p-value. So if alpha is equal to 0.05, so we need our p-value to be less than 0.05 for us to reject the null hypothesis. So the null hypothesis will say that the residual there's a normality. So we'll talk about the normality here. So here you can see we cannot reject the null hypothesis, which says that the error term is normally distributed. We cannot reject here. We cannot reject there. We cannot reject there. We cannot reject there. So the normality is okay. At least as far as we saw, this is fine, that's fine. That looks fine, that looks fine. And then this also looks fine, and that's also look fine. Even the first one, everything looks fine. So normality, we have no problem. The other thing that we need to test is we can now test for constant variance for the different. So we can test the constant variance for feed. Although we seems to see that the variance seems to be higher in feed E, but the analysis of variance, the test, the ANOVA test here actually tells us that there is no significant difference. Here we also seems to see no significant difference. And then, so the variance seems to be homogeneous in all our models. That is what we have here. But you have to be very careful with the tests, this tests here, because sometimes they can be very misleading. So so we can test for homogeneity of variance using the Levin test. So here we also see no significant difference. We see no significant difference. It seems to see no significant difference. So what this one tells us is that for the different the error does not vary between the feeds. The error does not vary between the cows. The error does not vary between the milkmen. Although although you can see from here there seems to be variation, but the test actually tells us otherwise, that there is no variation between that. So what always happens that people now go and test this, what we call you check the ratio of the maximum variance to the minimum variance in a group. And if that ratio exceeds 5, then you declare them to be significantly different. So we are not basing our test on this. We are now going to look at just the ratio. So if you look at feed, so this is what we have here. I'll try to explain this one here either tomorrow or today if we still have time. We have about an hour remaining, but probably it will be better to run this thing in the morning. I'll give you opportunity to go and run it yourself. And then in the morning, just briefly, I'll go over it, and then my colleagues will move. So for the feed, the ratio of the maximum variance in each group to the minimum variance. So if we look at this, for example, okay, so if we look at this, let me first clean this one off. So when we look at this, if this is the maximum variance, we divide it with the minimum variance, say this one here. We're saying if the ratio of maximum to the minimum is greater than 5, then we consider that the variance is not homogeneous in this group here. And then we also come and do it here. We also come and do it here. So let's go and look at. So for the feed is greater than 5. So we cannot ignore this. So we can actually think that the variability among the feed is actually greater than 5. The variance is not homogeneous. So this is where issue of transformation may actually come in. For the cow, it's okay. We seem not to have any problem. But for the milkman, we have the value is 9.73. So this one is also an indication that there is a problem with the assumption of constant variance among the milkmen and among the feeds. I see one question in the chat. I see people saying this email should be added. Where are they being added? If I may ask, I also need to ask the same question. Where are the emails being added? Somebody is going to answer that question. Okay. So if somebody is creating a list, that is fine. So now, now I have this very interesting example. I'm going to introduce the concept of a factorial experiment using this very nice example. I think it's the right time to have. There's what they call the beer Google effect. That is people believe that beer affects mate selection. If you go say in a nightclub, this reminds me of a story that there was a gentleman who went to the bar. He had a photo of his wife in his pocket, so he would look at the photo of the wife and continue drinking. So somebody asked him, it looks like you love your wife so much. Why you kept on checking on her? I said, no, I got my wife from the bar when I was drunk. So when I start seeing her looking beautiful, I know I've drunk enough, then I'll go home. So that's what they call the beer go-go effect. So here is just a simple, I mean, this is just for illustration. It's not a true thing. So there is a nice book discovering statistics using R. So here they say an anthropologist is interested in the effect of beers on mate selection in a nightclub. So the rationale of the study is that after alcohol consumption, the subjective perception of physical attractiveness would become more inaccurate. So as you take more beers, what you consider to be attractive seems to actually reduces. So there will be a blur effect. Your eyes will not see very well. So the other question was, does this beer go-go effect depend on sex? So we have two factors here. We have the effect of the beer, and then we have the effect of the sex, whether it is male or female. Now, so here, this is how the study was designed. So you get female, 6 females, you give them what you call the alcohol-free lager, or alcohol-free lager. So you get like exactly, it looks like alcohol, everything, the ingredient, but it's 0% alcohol. So this is like the control. You get 6 women in that category. You get a female, give them 2 bottles of beers. In that category, you get female, give them 4 bottles of beer. And then you do the same for men. And then what they were doing was that they would take a picture, take a photograph of the person that the participant was chatting with. And then you get a pool of independent judges to assess the attractiveness of the person in each of the photographs. So what we do is we get a number of people, we take them to a bar, and if this is the group without, you could have one group without alcohol, and then after some time you take the picture that they're chatting with, and then you want to find out whether actually this one will have an effect on this or that. Please, I'm wondering if the notes we're talking about, I think the notes should be there. Please wait, we're going to sort that on issue. You'll get the notes. If it is not there, you'll get it. Okay, I'm assuring you with that. First, let's concentrate here before you look at the notes. I'm still with you. So unless you're telling me that I'm not good enough, my notes is better than me, then you can start looking for the note while leaving me here talking. Okay. So this is kind of a study that we have. So after the study, these are the part of the result. So if we look at gender, ignoring the alcohol effect, so we seems to see that in terms of the average, both the men and the women seems to be doing fairly well. The attractiveness between male and female seems not to be there. However, there seems to be a lot of variation among the males. Okay, so the male can I mean, through the attractiveness. Okay, now when you go to alcohol, you ignore the effect of the gender. You look at the alcohol. You actually see if you take no beer and you take 2 bottles of beer, well, we seems to be doing fairly the same. It doesn't seem to cloud your judgment. But once you take 4 bottles of beer, we seems to really having a problem. So the attractiveness of the mate reduces with the amount of beer, but it seems not to have an effect on the males. The gender seems not to be an effect. Now let's look at it for both genders separately now. So if we look at the female, it looks like actually the effect of alcohol does not affect the selection for the female. But for male, actually, 4 bottles, you can literally take anybody near you and to go home. Okay, so you can see there's a big difference here between that. So what we are looking at is that we are interested in studying the mate selection, effect of mate selection on effect of alcohol on mate selection, and then we're also trying to look at the effect of sex on mate selection, and then we want to see whether there is actually interaction between the two. So these ones here look at what we call the main effect. Okay, So this one look at the main effect for gender. This one looks at the main effect for alcohol. And then this one here now try to take into consideration the interaction. So we are saying the question is the Google effect the same for men and the beer Google effect the same for men and women? So this is an exploratory data set that we can do. The next thing, we can also go ahead and we look at just a simple mean and the 5-number summary. So if we look at female, for example, the median is 60, and then the mean is also 60. For male, the median is 60, and then slightly the male seems to be slightly lower than the female as far as the selection of mate is concerned. If you look at the maximum, the most choosy lady had a score of 70, but there was a gentleman who is really, really choosy, got a score of 85. So all the mate that one of the mate that person chose scored 85 in terms of attractiveness. Okay. So if we look at the at it in terms of alcohol, so no alcohol, these are the means and the median. 2 alcohol. So you can actually see that if you're taking 2 alcohol and taking 2 beer bottles of beer and taking no beer, actually seems to have completely no effect. The means and the median are actually simpler. The male even seems to be doing better than the female actually when they've taken 2 bottles. This is just the, sorry, I'm not bringing the main anymore. But now when you take 4 bottles, you can see the drastic decrease now. Okay, so there seems to be a bigger effect after 4 bottles. So 1, 2 bottles, you're okay. It does not affect you, so you don't need to run home after that. So in factorial, do we always consider interaction effect? And if the interaction is, do we forget about? Yes, the fact that you do factorial is because you want to study the interaction. And once the interaction is significant, everything else can go away. You talk about only the interaction. The main effect is not going to be of any interest. Okay, we can continue on that. Okay, so here, then if we look at gender by gender and alcohol, it's still the same thing. Female, none, female, none, 60, 60, 60, 62. Okay, 2 bottles. So actually the female seems to end up slightly, the median seems to be slightly. So if the female has taken 2 bottles, they seems to have a better choice slightly better choice than if they did not take anything. So it seems to have some small effect there. And then for the male, 2 bottles, none versus 2 bottles, similar thing. Okay, actually perfectly the same. And then if you look at male and female 4 bottles here, so female no and male, female none and female 4 bottles, there's some slight difference here. Okay, and then if you look at the male, none and male, after 4 bottles is just disaster for the male now. So they literally, the attractiveness completely goes down. Okay, so but these are the things that you need to explore before you go to do any data analysis. You really need to be able to actually tell what is going on within your data set. So the importance of exploratory data analysis, because it helps you to choose the model later on. It helps you to identify if there are outliers, helps you identify if there are errors within the data. Like for example, we thought there could one of the milk in one of the milkmen seems to have changed the figures. Okay, so the first thing, of course, that we can do is our interest here is in the interaction, but we can just do a one-way ANOVA for each of them. So here, if we only analyze attractiveness explained by gender, you see the p-value is 0.3525. So that means we failed to reject the null hypothesis, and we say the choice of mate for male and female is actually the same, okay? And then when we come and look at alcohol, okay, then we see a p-value of 2.88 times 10 to the power negative 5. So this value is the same as 0.000283. That is the negative to power 5. That's more or less what it is. So this is much less than 0.05. So there is actually the effect of the of alcohol is concerned. Then you can go and plot, use this to plot the gender. You can see the effect here. So this is the gender, the female, more choosy slightly than the male. And then, but you can see this is the confidence interval, and the confidence interval of the two are just matched together. So there's no significant effect. Here we can see that no difference between none and 2 bottles, but there is a big difference between the 2 and then the 4 bottles. So that is what is giving us this significant interaction. So the next thing that we do then, we are going to run the real factorial analysis. So here we have now the main effect here. This is the main effect gender is 0.1613. This is greater than 0.05. So there's no effect of gender. Alcohol is less than 0.05. So there is effect of alcohol, and then the interaction is significant. So what we're saying in this case that once the interaction is significant, we don't need to bother about the main effect, okay? Because what that implies is that the effect of alcohol on choice of mate or attractiveness of mate depends on the gender. That's what I'm saying. And that's, you've been struggling with the coding, with doing the dummy variables, is because you want to see whether you need the same model for the different levels of a factor, or you want the same, or you have the same model. We have different models. So in this case, now if we look at, so this is what actually is telling us that if the comparison of the beers are done, if the alcohol comparison are done for female, there is no significant difference. If it is done for male, there is significant difference between the 2 and then between the 4. So that is what we have, and that's the interaction. So what we're saying in this case, if you ever want to talk about the effect of, you talk about the beer gogo effect, please treat the male and the female separately, because the interpretation result depends on the gender you are dealing with. That is the actual interpretation of interaction. So then you as a scientist, then you need to explain what is going on there, okay? So you could ask, maybe the females actually are not taking the beers. If they say you give them 4 bottles of beer, they could pour a part of it, but that's now a different thing altogether. So the interpretation now will depend on you as an expert. For me as a statistician, I would have done my part. I do the analysis, I hand for you the results, and we can brainstorm, we can do something, but you need to come up as an authority, and then you can do that, okay? So are we still together? Can I see? Okay, yes, that is good. Okay. Okay, so after we have done the analysis of, remember what analysis of variance does is just tells us at least a pair of treatments are significantly different. It doesn't actually tell you which of the pairs of treatments are significantly different. So if we need then to go and do what we call post hoc, or people say post ANOVA test. So the question is then, which of the pairs are significantly different? Okay, Annette to say, is residual the same as error term? Yes, that is what is always residual and error are used interchangeably. Thank you for the question. Okay. So one way of doing a post ANOVA is to run what we call a contrast. So a contrast is used when you have treatment sets that have kind of good structure in them. So instead of comparing individual treatments, we actually compare groups of treatment. That is what we do in what we do in contrast comparison. So for example, what we could do, we could have a contrast of no alcohol versus some alcohol. So you can see no alcohol is one treatment. Some alcohol can either be 2 or 4. So the average of 2 or 4 bottles. And then we can also have 2 bottles of alcohol versus 4 bottles of alcohol. And then we can have male versus female. Now, for each main effect, for the main effect, if the degrees of the number of contrast, independent contrast that you can run is actually equal to degrees of freedom for the treatment. So if I have 5 treatment, I can run 4 independent contrasts. In statistics, they call it orthogonal contrast. So orthogonal contrasts are contrasts that present totally different information, independent information on the comparison that you want to have. So I'm going to go through with you briefly how to construct a contrast and how to explain how a contrast works. I used to like GenStat a lot because GenStat used to do for me very nice contrast, but now ARA does a lot more contrast than GenStat. Now, the thing here is a little bit different. First thing that you need to do is you need to look at what do I want to compare. So here, for example, we have for alcohol, we have 3 levels. We have none. That is when somebody has not taken alcohol. We have 2 bottles, and then we have 4 bottles of alcohol, 4 bottles of beer, for example. Okay. So if I'm going to compare none versus that, of course, let's say this is the mean of none. This is the mean of 2 bottles. This is the mean of 4 bottles. Okay. So what I'm going to do, I'm comparing the average of this with that. So and my null hypothesis would actually be like the mean for none is equal to the average of the 2. Okay, you cannot compare 1 versus 2. You can compare 1 with the average of the 2. That is how the whole thing starts. Okay. But what we could also do, instead of dividing this by 2, we could also multiply this one by 2. Then okay, so the same thing can be 2 mu n should be actually equals to mu 2 plus mu 4. Okay. Okay. So that is more or less what you have. Then, of course, if we are saying this 2 mu, this is the same as that, we could also have it the same as this 2 mu n minus 1 times mu 2. Okay, let me first remove there. Okay, minus mu 4 should be equal to 0. Okay. Are you following what I'm trying to do? Okay, yes. Okay. So that is what I want to explain why I have this. You see now under contrast 1, I have -2 for that, and then I have +1 and +1. So this is the same as 2 times mu n minus 1 times mu 2 minus 1 times mu 4 equals to 0. Okay. So if I'm going to look at the coefficient in my comparison, I'm looking at the coefficient. This is the coefficient. This is another coefficient, and that is another coefficient. Okay. So and the rule here is that the coefficients should sum to 0. So -1, -1, 2 plus 2, and will give you 0. But it doesn't matter which of the two side takes positive and which of the two side takes negative. So 2 -1 -1 is perfectly the same as -2 +1 +1, because it will still add to 0. That's what we have. So what we want to do is then you get your data set. We're going to do this at some point. You get your data set, say, get this compass contrast, and then give us this. Say, I want to have 2 contrasts. The first contrast here is, and what we are contrasting here, we're contrasting alcohol. So it will be 2 -1 -1, which say compare none with the average of the first of these 2. And then the second one is 0 -1 -1. That means I'm no longer now interested in that. I'm only now comparing 2 and 4. So these are the 2 contrasts that I have. And then once you've done this, then you go and run your analysis as you have before, and then you actually see the interpretation results. So here we have, for gender, we want to compare male versus female. Okay. So now this is we have a model here. So we have gender. Remember, gender, we said it was not significant. Alcohol was significant. The interaction was not significant. Now, after doing the same thing, but when the contrast is already in, if you use this command summary.lm, it's going to give you something that looks like this. So here you have your gender 1. So gender 1 is when it is the one talking about comparing male and female. And remember, gender 1 comparing male and female, it was not significant. Now, alcohol 1 is this one here. So alcohol 1 compares none versus some alcohol. And then that is significant. You can see from here. Okay. So we saw from there that at least alcohol and no alcohol. The next thing we are going to say, okay, let's look at those who drink alcohol. Is there a difference between them? So the next one is alcohol 2. Alcohol 2 is highly significant. So that means there is a significant difference between 2 bottles and 1 bottle. That is what you have here. And then the most interesting one now is the interaction. Remember, we say gender 1, or we say alcohol 1. Remember, alcohol 1 compare none versus some. Now, with interaction with gender, we're saying, okay, if we are comparing none versus some, Is this comparison the same for male and the same for female? So this is the interaction now. So that means if you look at the female versus the female, when you're comparing none versus some alcohol, there's interaction with the gender. That means the comparison within the male will give you a different result from the comparison within the female. Remember, when we went back here, we saw that within the female, there was no interaction. Within the male, there was interaction. So remember, it was none versus some alcohol. Okay, so it's none some alcohol. So this is the interaction that we are talking about here. So we are talking about none versus alcohol is significantly different for the male and the female. Now, then the next one is gender 2 interaction with alcohol 2. So we say 2 bottles versus 4 bottles is also significantly different for the male and the female. Let me check some question here. When do we use post hoc? We only use post hoc when the analysis of variance tells you in the significance analysis of variance. Okay, so that is what we have here. So this will test for you gender, male and female. This will test you no alcohol versus some alcohol. So it could be born again versus Catholic. And then this one could test for you Catholic serious drinker and Catholic mild drinkers. Please don't get offended. I'm also a Catholic. And then this one then can test you the interaction. If we are comparing alcohol versus no alcohol, we look at the gender. Does it matter which gender you're in? And this case said yes. If you're comparing male and if you're comparing some alcohol versus no alcohol, in female, you're going to get no difference. If you compare in male, you're going to get different. Then the next one is if I compare 2 alcohol versus 2 beers versus 4 beers, in female, I will see no different. In male, I will see different. So this is now a more detailed analysis that you've done after this. So this one will just tell you the significant interaction between alcohol and gender. But this one now tells you where the interaction is coming from. Okay, so here you still have the residual, you have the degrees of freedom, then you have the adjusted, and then you have the R square, we have adjusted R square, and then you have the p-value. And so I remember somebody asked, what is the role of contrast in comparing, to compare post-hoc tests compared to, well, what I'm saying is that contrast is a part of post-hoc test, but contrast is different in that is the choice is your data set, the set that you're trying to compare has a much clearer structure that right from the start of your experiment than, for example, in a situation where you just get a bunch of treatment and you want to see which one is doing what. But in this case, your comparison is very clear. You want to compare alcohol versus no alcohol, some alcohol versus that, male versus female. They do the same work, but they give different amount of information. You get totally different in-depth amount of information that you have. Okay. There's a paper we published in 2019, Odong et al. It talks about the use of different statistics in writing papers. You can have a look at and see. Okay, so the other thing is once you have a significant, interactions, what they always say is that then we go and actually explain what we call the simple effect. So the simple effect is what we say, you make comparison. Can I compare alcohol versus no alcohol for female? And I compare the same thing for male. So simple effect, so the significant interaction of 2 factors implies that the effect of the 2 factors cannot be interpreted independent of each other. You cannot look at them, you cannot look at alcohol independently from gender. You cannot look at gender independent from alcohol. Because if you look at At gender independent of alcohol, gender will tell you that there's no difference. Okay. So simple effect comparing level one factor when holding the other factor constant. So I can compare no alcohol versus 2 bottles for female, holding female constant. I make comparison for female. I can do the same, no alcohol versus 2 for male. Now, this is what we call a simple effect. So a simple effect is like we are running analysis of variance comparing no alcohol and alcohol with the data for female, and then we also do it with data of male. So you compare male and female at 0 alcohol, or compare male and female at 2 bottles of alcohol. So this is what we call a simple effect. The choice of, we say, can we use post hoc tests for all types of treatment comparison if a number shows significantly? There has to be a choice. There are several post hoc tests that are there. So you need to be able to choose them. And their range of statistics, their range of reason as to why each one would be preferred over the other. I've just told you for the case of a contrast, for example, if your data structure is well defined, then a contrast actually gives a lot more richer information in that particular case. If, for example, you can make what we call pairwise comparison, where you compare all the different pairs that are in your data set. So if you have 10 treatments, you're going to make like 45 pairwise comparison. The problem with that is this, what we call type 1 error. With the type 1 error, the thing here is that because type 1 error, it talks about, the amount of error or you're willing to accept for rejecting the null hypothesis. Now, for every comparison that you make, you're going to make type 1 error. So if you have several pairwise comparison, the implication would then be that you're going to have a lot of type 1 error that's going to be bigger than what you actually started with, or what you had set as your original value. So there are lots of statistics around post hoc tests that I would request you to read and come up with kind of a solution that you have. Okay. Okay. So what we are trying to do here is then we can construct a test for simple effect. So I'm going to introduce here. So here, for example, let's say we can compare female for none. Okay, so let's look at this. Okay, so remember, if we look at our table here, okay, we have here female, none, female, 2, female, 4, male, none, male, 2, male, 4. So I want to just have it here so that you can see exactly what's happening here. So let me first clean up this a little bit. Okay. Okay, so let's say this is female with a none, and this is female with 2, because the alcohol effect 1, gender, okay, and then we can have female, and then we have male. Okay, so here, okay, no, I think no. The thing is defined here. Sorry. So here I want to, let me just clean this one up, and then I can. Okay, so let's look here. This is what we define as our effect 1. I'm going to try to be as patient as possible. So under this, for example, we want to compare female none versus So, okay. So we want to compare, no, not female none. We want to compare none versus some. Okay. So we want to compare this none. There's none female, and then there's none male. Okay. So this on one side, and then let me get another color of my pen. And then we want to compare this because these are some. And then these are also some. Okay. So this is what we tested before. We compare none. So the none can come from male or female, and then the sum bottle can also come from male or female. So you can see from here we have -2, we have -2, and then we have +1, 1, 1, 1, and then you look at this, they all sum to 0. Okay. So this one will test for us none versus some. And then this one here would test for us, you see now we have, so ignore where there's 0 now. So this one will tell you, will test for us. So this is female 2 bottles, female 4 bottles, male 2 bottles, and male 4 bottles. So here you are now having two bottles versus 4. So the 2 bottles, we can get it from female. We can also get the 2 bottles from male. And then here we can get the 4 bottle from male, and then the 4 bottles from female. So this is our alcohol effect 2. 2 versus 4. Okay. Then the next one is gender. Gender. So here we have gender none. So here we're comparing female none with male none. Okay, that is gender none. And then here we're comparing gender 2. So you're comparing female at 2 bottles with male at 4 bottles. So these are the simple effect. And then here gender 4 bottles. So yeah, we fix the gender. We fix the bottle number to 4, and then we compare male and female. So this is a simple effect because we fixed the bottle to 4. That's why we are looking at female 4, and then we look at male 4. And then here we fix at 2. So female 2 and male 2. So remember here, male and female only. We are only interested in male and female with 2, male and female with 4. So there are only 2, one become negative, one is positive. One is negative, one is positive. So once you have this and then include it into your model, and then once you run the summary, you get so simple effect 1. Okay, so this is the alcohol versus no alcohol. That's alcohol 1. It's significant. And then here you have your alcohol 2, which is 2 versus 4 is significant. Then here you have gender none. So gender none is you're comparing male and female when there was no alcohol. Okay. Gender 2 bottles also is not significant. Male and female, when there's 2 bottles, their choices are similar. Male and female, when there is no alcohol, when there's 2 bottles of alcohol, their choices are similar. Then this is the one where I said you're comparing male and female when there are 4 bottles of beer. There is a significant difference between male and female when there are 4 bottles of beer. So that is the value that we have there. What is the difference between multiple comparison and contrast? So multiple comparison, I mean, you're making several comparisons. Contrast can also be part of multiple comparison, but it's a special multiple comparison in which you have really, if you want orthogonal contrast, you have very fewer comparison compared to if you are making multiple pairwise comparison. What is the title of the article? What you need to do, just look for Odong et al. 2019. It is an African crop science journal. What's the title? Okay, that's answered. Okay, so what you can see from here is that you can then, okay, there's still some questions. What's the difference between alcohol effect 1 and 2? I didn't get. Okay, I will try to re-explain. Okay, so the simple effect alcohol effect 1, we are comparing no alcohol versus some alcohol, which is we are saying either somebody has taken 2 or has taken 1, the average of them, that will give us alcohol effect 1. Then alcohol effect 2, we are saying those who took 2 bottles versus those who took 4 bottles. That is alcohol effect 2. And then gender none is we are comparing male and female if they did not take alcohol. If they did not take alcohol, male and female. Okay. So there is a, we have a survey monkey. Not yet, just hold on a little bit. I'm almost done, then I pass you over to my colleague, Ellen. Okay, so you have, so gender none, I mean, then we're saying if you compare male and female, when they have not taken the alcohol, the level of choice of mate is the same. When they have taken 2 bottles, the level of choice of male and female are also the same. However, gender effect 4, if male and female are compared after taking 4 bottles of beer, then you find that the female still choose very attractive male, the male choose very attractive, the male choices now goes IY. So they just pick anybody around and the day will go on. The conversation continues. So just a bit on the post hoc part of the post hoc. You can do what called a pairwise test. So this one is only possible if you have very few comparison. Like here we have only 3. We have none, 2 or 4 bottles of beer. So here what you can see, none and 4 bottles are significantly different. And then 4 bottles and 2 bottles are also significantly different, while this one are not significantly different. We are going to talk a little bit on about this tomorrow, just a shorter while. So you can also do multiple comparison with 2 case contrast. So here it can compare for you 2 bottles versus none. It tells us there is no difference. 4 bottles versus none tells you there's significant difference, and 4 bottles versus 2 bottles tell there's a significant difference. So that is the end of the slide. I can see if there are a few questions, but then I can hand you over to Ellen. So at least we have finished the bigger part. Ellen has already sent for you the survey monkey. Please, we request you to fill the survey monkey. It takes a much shorter time. We need this to evaluate. We need your evaluation so that other courses will be organized depending on the need that will arise, and depending also on your observation. We as trainers, we need to be informed of where we need to improve, where we are doing well. So please be as sincere as possible. Just take a few minutes, fill that one up. So tomorrow After that, I think we are not going to continue now. We have just 10 minutes. We can give you to fill up the questionnaire in 10 minutes. And then we also are planning to do a small study. I'm going to talk about it tomorrow. Yeah, but please run the script. Your assignment is to run my script so that tomorrow in the morning, we will not take a lot of time so that we can give you more knowledge if you can do what we have. Please fill up Survey Monkey. I would love to see all the people today filling up the Survey Monkey. Okay, as you fill in, I can answer a few questions if they are there in the Q&A. The link has been shared. Let my colleague check whether the link is actually there, but the link has been shared. Yeah, so the Survey Monkey is being shared now. Please first fill that one there. Just click on and then answer. So I expect everybody to be silent now to answer the questions. Tomorrow, sir. But you have the script and the data set already with you. Just run it, and so that when I come tomorrow, we will continue from there. Tomorrow, we should be able to take less than 40 minutes to have it done. The correlation script should also be somewhere on day 5 or day 5 folder. Yes, it's also on day 5 folder. Are we going to do any PCR? No, time may not allow. We are planning in future to do a training only on multivariate analysis. Yeah, so the next one is going to be more specialized. So you need to keep hold on. Somebody's asking about physical training. Physical training, if you can walk over to Makerere, that's fine. You can come to any of us and then ask for to be trained. I will be more than honored to train you. Oh, okay. I need to, but it would also be to get what I actually realized that when I was combining my creating that data frame, the treat the what I call treat that I used was actually the wrong one. So when you change treat, you change that final step. But you'll get, I will share with you. We want to see 165 questionnaires for people who are there today. Please share the link again, those who have. Have you finished filling in the questionnaires? How many people have finished? Done. Okay, thank you for appreciating our team. Say behind every successful man, there are women. So I have 2 of them behind me. Said other software, please. SPSS starter are paid packages. They are getting outdated. ARA is the in thing now. So you need to run ARA. You don't have any other option apart from running ARA. Yes, Python is also very popular. So you get yourself any of those, you are good to go. Yeah, it's also. So if you want us physically, you organize with your university to give us air ticket and come and a place where we can sleep, we will come. Yeah, you have exam in ARA next week. This is very helpful. We are happy if we can help you. If you become the director of research institute in your country, please remember us. Somebody asked for the link of the survey. It has been put again and again. Yeah, so tomorrow we are going to finish probably a bit early, but we are really grateful that you've been able to persist throughout the week. It also gives us a lot of energy. One, if we see you're also still there, because we cannot teach ourselves or teach 1 or 2 people. So the fact that we still have 160 plus is really good. So thank you very much and see you tomorrow. God bless you all.